So, dear colleagues, I think we can start already. And today the first lecture will be given by Dr. Elena Saveleva from the Institute of Russian Academy of Science related to safety of the atomic energy. And the topic is geological disposal of radioactive waste. So, please.
Thank you. So, good morning. I was asked to make this lecture on geological disposal of radioactive waste. I don't know exactly what was expected from this lecture. And so I collected what I had around me and made some presentation, which I am going to present you. So what we know that nuclear energy is clean energy. It doesn't emit greenhouse gases. But ordinary people are all afraid of it because of radiation and so on, and especially concerning the radioactive waste, which can be potentially dangerous during long periods. So the problem of radioactive waste arose and then were proposed several different possibilities how to manage with it, starting with launching it into space, disposal in ice shield in the ocean. All of them were considered as not exactly good. So at the moment, the geological disposal, so storing in the deep geological rocks, deep geology, is considered as the international consensus. And storage is considered only during the period when the final disposal is constructed. So to understand everything, first we'll start with some terminology. So what is disposal? Disposal, it is the placement of radioactive waste or anything else in some facility without intention to take it out. And it is considered with some aspects of producing safety for environment and humans. So there is no intention to take it out, but during monitoring or during constructions, there can be some accidents which need make it need to extract something. So it is the terminology, but all facilities are tried to design so that the possibility of extraction of radioactive waste is possible. So now about safety. Safety is considered with those impacts on population and environment during the all long period. And it is normalized by special limits which are considered as not danger for the humans. And this safety is fulfilled by safety functions of the disposal facility. Safety functions are, global safety functions are containment, which deals with retention of radionuclides in first matrix, then in container, then within the engineering barriers. And isolation, which is, it deals with the deep position of the disposal so that the time of getting the radionuclides to the biosphere is as long as possible. There are different types of host rock which are usually considered. Most often they are crystallines, salts, and clays, but also compacted tuffs and other compacted sedimentary minerals also can be possible. So first, there was the consideration that two qualified geologists and one engineer can construct the design and construct the facility. But now more than 20 organizations take part in our project, and it is the overall situation. Lots of scientific and technological and design organizations are incorporated in such projects. And mostly it is connected with the problem that safety is not only expected to be, but it is also needed to be justified for the people. So the main problem of the management of radioactive waste is the justification that the designed facility is met with the safety requirements. And for this, there is a special procedure which is in international community called safety case. So what is the safety case? It is something, maybe document, maybe procedure, and the main problem is to set all arguments which are in the favor of the safety. And all these arguments need to be proved and justified. And this can be made only by application of numerical modeling, because no experiments could be so long as the potential period of radioactive waste, the potential danger of radioactive waste. And also there are limited number of possibilities that can be considered. So we need the numerical modeling, and also this process of safety case and is iterative, because gaining more information, we need to use the new information to incorporate it in the previous estimates and so on. So for numerical estimates, we use the safety assessment. It is the main part of the safety case, and you can see here the basic scheme of the safety assessment procedure. It includes gathering and collecting and analysis of different kinds of data and different kinds of aspects which are called features importance processes. It includes construction of scenarios. It includes description of initial state, and then it includes development of corresponding models, their validation, and also the performance of multivariate analysis. And all these stages incorporate the management of different kinds of uncertainties. I don't stop on uncertainties. The next lecture is about them. So safety case and safety assessment is performed on all steps of the life cycle of the project, which starts with site selection. Usually, it is in many countries, the site selection started with checking all the territory on the possibilities, on the negative factors which can be dangerous for the deep geological disposal. So here are presented some possible negative factors. After all territories with negative factors and with specific land use are excluded, can be selected some regions where such a logical factor is considered, so there is agreement with the human population and the authorities of the region, and it can be started there the more detailed investigation to consider if there is the host rock which meets with basic features important for the disposal facility. And after considering several examples. Also, some economic factors, if host rock features and others seem to be equal, economic factors can be also considered. They mean the ready infrastructure and the distance to origins of the radioactive waste. So in Russian Federation, we have a selected site, which is in the Krasnoyarsk region. You can see it in the map, and some information about it. So it is 26 kilometers from Krasnoyarsk. The host rock is considered crystalline Archean gneiss. The depth is about 500 meters. There are planned galleries about 5 kilometers. And the constructions of the surface facilities started in 2018, and this year, in 2023, mining works started in this place. This site has the license, the national operator has the license on construction underground research facility, and underground research facility will produce the information on if this site is really adequate for the deep geological disposals. At the moment, the site is considered as potentially approved. So to construct the deep geological disposal in Russia, we developed a strategy which took all the phases, and each phase is characterized by different aspects, and these aspects concern with design, with personnel, with sociological impacts and others. As now my institute is a scientific guide of the project, I'll mostly stop on the aspects which concern with long-term safety and safety case. So the first three phases of this strategy are devoted to underground research facility. And now we are starting the phase 2. As I told, we started the construction of this facility. During pre-construction activities, there were additional activities at the site, investigations of geology, deployment of monitoring networks, etc. And also, during this period, we constructed the national platform for the radioactive waste management. We started issuing a journal which is called Radioactive Waste. It has more than 40 papers concerning underground research facility, but there are also other articles on other topics concerning management of radioactive waste. It is issued in paper in Russian, and also there is a website where English translation is available. The other important part was the development and detailing of research and design program. It started with information which we had. It mostly were recommendations of the experts obtained during the license period. Also, we considered requirements on safety, both international and Russian, in legislation documents. We considered international FEB catalog, and also we asked modelers which parameters are important for their nuclear models, the first estimate on what they needed. So the first step was considering basic directions of investigations, which then were distributed according their position and time. And now we are continuing development of numerical models and informational model for underground research experiments. And also, we developed special investigation programs which are now going on. I'll talk about them in more detail later. So the basic structure of R&D program is the matrix, where columns are parts of the disposal facility, such as geosphere, engineering barriers, radioactive waste, equipment, and biosphere. And rows are types of activities, which include monitoring, technology development and demonstration, theoretical analytical analysis and modeling, and field research and laboratory experiments. In the cells, they are presented the directions, which then can be presented in the hierarchical scheme down to experiments and more detailed investigations. So this program is part of our informational system, informational support system, which is called PULSE. And for each research, there is a passport which presents a description of the investigation, type of it, and also there are lots of contact information on results, on reports where the results are presented, on publications, on raw data. The specific type of passport is for those experiments which are expected to be done in underground research facility. For them, there is more detailed description, which contains also requirements of the experiment, some measurement equipment, other equipment, requirements on supplies, and also for some of them are presented results, presented visualization from information model, which indicate how equipment is stored, how it is connected with supplies, and etc. So now I'll stop in a little bit more details on those special programs which are under investigation at the moment. The first one and the most important is scientific support of shafts and tunnel mining. So several more words about underground research facility. It is designed as some surface buildings which are placed in the vicinity of the shafts. There are considered 3 shafts: technological, ventilation, and auxiliary. And the depth of the shafts, as I already told, is about 500 meters, and their diameter is 6 meters. And the contour of tunnels, it runs around the place where the disposal is considered to be constructed. In the tunnels, there are places for chambers, for experiments. They are placed based on preliminary analysis of the geology and the requirements of the experiments about which I already told. So the scientific support is the time when we get the valuable information on the geology, which can be obtained only before grouting of the walls. And also these scientific activities shouldn't slow down the mining work. So we need to somehow consider the most important investigations. So for this purpose, we divided the activities in 3 blocks. Block 1 is investigations, they are called regular survey, and they do not can be made in the parallel with mining, and they do not interrupt significantly the mining, and so they are incorporated in the cycle of the mining works. Block 2 is the part which is the most slowing for the mining works, because it considers drilling some additional boreholes in different directions from the shaft, performing investigations, and so it requires the more detailed planning. So when we go down and we come to the position which is planned to be point of the interval investigations, we need to schedule these investigations to make conclusions on what real investigations are planned in this position, and what, I don't know why it is, maybe there is timing. What are going on and what equipment we need. So we need to be prepared so to not slow to so that minimize the period for which the mining works are stopped. So I didn't had told about the block 3. It is the monitoring and additional investigations in the boreholes constructed during block 2. So it doesn't interfere with the mining also. So it doesn't slow down the works. So the block 1 is considered with geological documentation, all kinds of documentation, describing photo, 3 laser scanning, fracture measurements, and all this information is stored in the informational model. The example is shown here. And the other part of regular investigations is sampling the outcrops and water samples. And these samples are also described, and the information which is in the description is also immediately stored in the special databases which are connected with the informational model. So this is the schemes of the informational model, how they look like now. They are constructed on the information obtained during drilling boreholes at the positions of the shafts, and the descriptions of cores, and by green rectangulars are marked places which are considered as preliminary positions for interval investigations. And when coming to them, these are positions which are connected with some discontinuities, expected fracture zones, expected zones of high conductivity, and so on. So these are not some disturbed zones. And now, after going down, when we came to the position, we put the direct place in the informational model, which stores all this information and the results of the investigations. So the main goal of interval investigations is to characterize the quality of the rock. Mostly it concerns with strength properties and water permeability. For this purpose, planned to drill some special boreholes, which are planned to be studied with acoustic and video logging, and also mini seismic apparatus, and also some slots are considered to be used for stress strain estimations. Also, during interval investigations, if it is a fracture zone, fracture properties will be considered, and fracture feeling samples will be taken. And what is also important, during interval investigations are planned the analysis of the construction disturbed zones, especially their depths. It can be made by mini seismic operators. In the bottom of the slide, you can see the number and the length of the boreholes which are planned for interval investigations. So for investigations of disturbance zone are planned to use the acoustic mini seismic method, which was successfully used in the Monterey Rock Laboratory in Switzerland. You can see here the apparator, the equipment. It works as the acoustic wave is launched, and then when getting to the damaged zone, it is reflected and then obtained by the high active receiver. And then the results are analyzed, and the distance and the features of the damaged zone are presented. So the strain estimation is planned to be performed by slot discharge layout. Here you can see how it is done in other places and what we consider to perform in our walls. It is based on the comparison of measurements before the slot is drilled and after the slot is drilled. And the magnitude of stresses can be estimated by the formula which is presented here, basing on these measurements. So the second part also concerns site investigations. During the preparation phase, we deployed the monitoring system, which contains different types of monitoring: geodynamic, seismic, hydrological, hydrogeological, geomechanical, and meteorological. Stations are placed on the site and the surrounding territories. In the slide, you can see some measurement posts, and the information obtained by monitoring is already analyzed and used in some development of models. During summer periods, we on the site were performed additional investigations concerning the hydrogeologic tests. And before hydrogeologic testing, the acoustic lodging was performed in the wells to detect the fracture zones. It was made by Russian equipment Parus, you can see it there, and it is supported by software which allows to distinguish the fracture zones with higher hydraulic conductivity from other anomalies, and they are placed there in the chart, these zones. And they were afterwards confirmed by hydrogeologic tests. This is the equipment for hydraulic injection and filtration tests. And it was performed at some wells to detailize the conductivity coefficient. And you can see that the conductivity coefficient obtained in 2022 is much lower than the one which was estimated during the preliminary phase. It was expected because the modified and renovated equipment and strategy for measurement was used. This is equipment for rock quality assessment. These acoustic and optical televiewers are considered to be used during the mining procedure in the interval investigations, and also it is used in the wells which are drilled during the summer period for additional investigation of the surrounding zones. During drilling, cores, oriented cores were sampled. You can see them. There are lots of non-disturbed cores, and acoustic televiewer together with incrementary allows to check the more damaged zones in the well. Also, using televiewer which makes snapshots of the wall, and then using the special software to present them as panoramic view and detect fractures from these images was used, and it allowed to make some statistics on fractures, which can be further used for development of DFN models. Also, for cores and for outcrops were made some laboratory tests, including tomography. Also tomography with high resolution, and making it together with electronic microscope allowed to construct mineral composition, maps of mineral composition. So geology is important, and the second part, coming closer to the radioactive waste, is engineering barriers. And our program to investigate the engineering barriers includes three intersecting activities which deal with selection of materials for engineering barriers, selection and justification, and studying geotechnics to produce the constructions from the selected materials, and also investigations concerning the evolution of these materials at the within itself, basing on the interactions of thermal and other chemical processes, and more interesting are on the contacts with different types of barriers. The scheme in the bottom presents also this interaction of these investigations, starting with concept and by modeling the performance of the engineering barriers, we can construct the requirements on materials. Then we checking technological feasibility, we can answer the question if it is possible. Also having the technological limitations, we can estimate what are the proposed types and design of the engineering barrier system. So all this modeling and justification of materials is based on the safety functions. For example, we can consider the safety function of the clay buffer, which is the usual part in the deep geological disposals within crystalline rocks. And these are local safety functions, especially prescribed for the buffer. And they need to be connected with the global safety functions. And they are they perform they give the performance due to the special features of the materials which can be used. So for buffer, it is important that it provides the favorable conditions for the radioactive waste container. So to stop or to slow the corrosion and to help in ways when the mechanical stress from the rock is too high. It somehow connected with the global safety function of containment. So we consider that the container is fulfilling its is connected and is hermetic during the most long period as we can wait. And the other part is connected with the global safety function of isolation, which deals with limitation of and slowing the migration of radionuclides in the buffer. So to support these local functions, we need special features which need to be presented in the buffer materials. You can have a look and see that all these features are presented and are characteristic for bentonite clays. So the most often for buffer material is considered the bentonite clay. But real numerical description of how these characteristics are presented in the real materials need to be justified by additional investigations of all these properties, so that they can be used for proving the performance features of the buffer of the disposal facilities. So all these features for investigations are divided into groups, and these groups are started to be investigated in different organizations. Lots of them are presented in the slide where organizations were named, and some results are already obtained. Some models using these features are constructed so that the description of the buffer buffer is made, and real requirements and their meeting with real materials could be made. So this is the slide presenting some laboratory equipment and two layout tests on such important features of the bentonite as self-healing and erosion and generation of colloids. You can see the design of the layout and some tests which were performed in the laboratory. So when we have the requirements which we need, we also need to find the raw material which can be used to make the constructions for our disposal facility. It requires to have a possibility to supply all our amounts of material and also produce the raw material of containing the features and properties which allow to technologically perform the constructions of the required with required properties. So for this purpose, geological studies of the clay deposits was performed, and at the moment, the most preferable is the set of deposits in the Khakassia. Here you see the slide of the deposit which is now actively working. It is called Desятый Хуtor. But around there are other deposits which are meant to be used for as a supplier for the geological disposal in the Krasnoyarsk region. It also has some infrastructure for producing the compacted constructions. So, and there are layers with bentonite of rather high quality. Also, this bentonite is characterized by high stability, which is also very good. So now the last part of my presentation, I already mentioned the system PULSE. It is the Project Underground Laboratory Scientific Escort. It is a set of databases and which incorporate all kinds of information which is obtained during the project. And its main purpose is to provide the traceability of safety arguments, which is made by using the special metadata approach and lots of connections, as I already showed you when showing the investigations. Each research and each model and each other activity are connected with FAB system, with position in the research program, is connected with some documents, etc. So the one part which is PULSE linked is what I also mentioned, information model. Here it is presented in more detail. So for the model of underground research facility, you can zoom each part and then see what is placed there with different types of the of detailization. And while getting down and making real information. It will be also filled with the results of investigations, and the structure will be also changed. The chambers and points of interval investigations will be placed in their real position. Pulse and informational model are also connected by when making numerical models of the experiments, which is very important for optimization of placing the detectors and checking if the experiment is really going to obtain the results which are expected. Here is the slide how this connection is made. In Pulse, we have lots of descriptions on the experiment. In informational model, we have structures. Structures allows us to get the geometry of experiment and getting information on the how it is going to be performed, the regimes, the places, and characteristics. We can make a model, and then the results of the model can again be visualized both in Pulse system or in informational system. We performed the numerical modeling of the experiment concerning the thermomechanical features of the rock. And here you see the modeling. And we also performed sensitivity analysis, which showed that we really obtained the estimates of features which are expected from the experiment, and also that the most important is to preserve the values of the heater generating. Also, we are considering as our ambition to make the digital safety case within the Pulse system. It is some type of perhaps Wikipedia-like document with lots of connections with already presented documents, with results down to real raw data and descriptions of how these raw data were obtained. So to present the traceability of all safety case arguments, and to make all connections with all types of different information which is gathered within the system. So for modeling, we need to use the program codes which are approved by our regulator as allowable for these types of numerical calculations. So programs called FENIA, which is the for thermomechanical modeling, the transport of the heat, the temperature, and estimation of stresses, and stresses taking into account the thermostresses. And program Corrida, which is for estimation of doses at the final part of the modeling, and also the behavior of the radioactive waste itself within the matrix. These are under the consideration of the regulator, and code GERA for groundwater flow and transport modeling is already approved for these types of calculation. For chemical modeling, we use FreeQC code, and we developed lots of different models of corrosion of steel, of behavior of the concrete of behavior of bentonites, on sorption, on releasing of the radionuclides from the matrix, but all of them mostly are based on literature raw data. So for using them for our safety assessment, we require additional results of laboratory and layout experiments, and to validate these models on data concerning our materials. And all of them are encircled by the code mouse, which allows to estimate uncertainty and deal with different types of uncertainty. This is the this is the part of the next presentation. So using Gera code, we can incorporate faults in the model of groundwater flow and transport. We can consider DFM modeling, which makes the structure of fractures and faults, and also consider migration of radionuclides into matrix. And all these alternative models allow us to construct and consider the type of conceptual uncertainty of our zone around the disposal. We have several models of faults, and also we have several approaches how to deal with them. But mostly developed is the 3D transport, groundwater and transport model, considering the efficient coefficients, efficient porous coefficients. And for this model, we performed sensitivity analysis to show that most important for the transport, for the flow and transport, are positions of the faults. And that faults require investigations concerning if they're really positioned here, and also if they on the type of their hydraulic properties. So that's all what I can say for a moment according to the works which are performed for our deep geological disposal, and what I understood as the topic of my lecture.
Any questions?
First, thank you so much for your presentation. I'm asking about the mechanical properties for buffer. You said that it's self-healing, so I need more explanation about what self-healing means and what the properties that affect it to be self-healing or not.
Here we consider as self-healing the healing the fractures, so that the bentonite clay is swelling and the fractures are closed and they don't interact on the transport and other features of the buffer. So self-healing is closing of fractures by swelling while dealing with water.
Any more? Just one short question. What is the depth now of this tunnel? Or this well?
Unfortunately, it stopped very close after starting because of some problems with the organization which started the mining.
Mhm.
I don't know exactly, but we came up to the gneiss, but didn't start with them.
Okay.
Thank you for your presentation. I'm from China. I have a question to you. How often do you update your safety assessment and your safety assessment for your repository?
What?
How often do you update your safety case and the safety assessment for your repository?
We perform direct and full safety assessment for each point of the new licensing. We perform safety estimations more often, exactly when we get new information which can be incorporated and which, on our point of view, can add something to our modeling. But real total safety case is performed for licensing.
Any more questions? If not, then thank you again. So now we'll have a short break and then the second lecture.
принципе, формально достаточно глубокий, чтобы подать ученым брать. Раз, раз, раз. Да, слышно?
So, dear colleagues, we continue. And the second lecture will be given by Valentina Swidelman from Institute of Academy of Russian Academy of Science on safety of atomic energy, and it will be about uncertainty management for the long-term radiation and environmental safety assessment of radioactive waste disposal. So, Valentina, please.
Excuse me, has the lecture started?
Okay, sorry, I forgot to turn on my microphone. So, where was I? The international consensus that the right way to deal with radioactive waste is to isolate it in the deep and stable geological formations, employing multiple both natural and engineered barriers, and this will provide safety for the long period of time. The catch here is that performance of such a complex system with multiple barriers, with multiple elements of each barriers, with huge variety of relevant to safety processes, need to be thoroughly assessed. And we need to be sure, and we need to demonstrate that all corresponding uncertainties are dealt with, and we are sure in the results that we are obtaining. So, as I said, our background of our problem statement is that first we have some objects, radioactive waste, which is potentially dangerous over long time scales. Also, there is a commonly recognized principle today that we should not impose undue burden on future generations. So we need to deal with this problem today, not tomorrow, not the day after tomorrow. We cannot rely that future generation could manage with our waste. We need to be sure that it's safely managed by ourselves. So safety assessment is comprehensive analysis of the performance of this system and assessment of remaining hazard associated with our disposal facility. And uncertainties in this process are almost everywhere. They are inevitable. And if we manage uncertainties adequately, if we can justify that we assess them, this is a huge step. This is, I'd say, cornerstone of confidence in the results of our safety assessment. So let's formalize a little bit the problem statement. We need to predict evolution of huge and complex natural and technogenic system over a long period of time. And this task could not be done without numerical modeling, because we just have no such time to provide sufficient experiments for assessing this problem without modeling. And we need to manage uncertainties which appear almost in every step of our way. This slide provides a very simplified, I'd say, view of the processes that need to be simulated during safety assessment. As you can see, we need to consider processes in radioactive waste matrix. Then we need to assess how the contaminants could migrate through the engineered barrier. Then you should understand how this contaminant migrate through the geological media. And then finally, you need to estimate the potential hazard to the environment and people, and make sure that this hazard is not significant, that it will be safe for both environment and people. The main challenge here, apart from the already mentioned system complexity, that relevant processes are running in very different scales, both in space and in the time. So we cannot just develop one model. We inevitably need a lot of models for different scales. So how we deal with the uncertainties in general, and particularly in this situation. First of all, first step of uncertainty management in any field, in any area of knowledge, is to identify sources of uncertainty, because we, of course, cannot manage something that we are not aware of. For the deep geological disposal, sources of uncertainty, various sources of uncertainty could be classified in this way. First, we have uncertainties of system properties. In particular, they are rooted in inaccuracy of measurements, and also the huge deal here is natural variability. For example, if you measure, I don't know, hydraulic conductivity in several points near our potential site for repository, and then measure the same quantity in another several points near the first ones, the values will differ because geological media is heterogeneous, and it's our reality. The second type of uncertainty sources is our understanding of processes that run in our system. First of all, any model of any process is, of course, simplification, and you could simplify your system in non-unique way. And when you consider interaction of these subsystems, this non-uniqueness continue to increase. Here you can think not of something like jigsaw puzzle, but more like set of Lego bricks, and you could connect these Lego bricks in different ways and still obtain the model of the whole system, but it will be different models, and you need to assess uncertainties for all of them. And the third type of uncertainty sources in our case is events that could change the evolution of the system. And here the problem is twofold. On one hand, we design our system, we select our site for our repository in such way that events, external events, human intrusion events could be very rare. We try to minimize any appearance of external events in our system. But on the other hand, it's very hard to predict rare events because we have no statistics for them, and it's not easy to predict something that rare. So after we identified our uncertainties for each source or for each group of uncertainties, we should answer several pretty simple questions. First, could we quantify uncertainty numerically? Could we assess them? And the second is to what extent they are significant, and the final one, the main question, could these uncertainties be avoided ideally? Almost always no. But maybe in a lot of cases, these uncertainties could be reduced. So on this slide, you could see a little bit another view on the classification of uncertainty of the whole system. And the idea is the following: to describe, to predict evolution of such sophisticated system, you could use scenarios. This is postulated descriptions of potential variants of system evolution from given initial state. And when you described scenarios, then you could decompose each of them into specific set of models of processes or models of subsystems, and you then could again assess uncertainty of this scenario and corresponding models numerically. I'll say this on this slide because it is tiny but very important remark that there are several terms, several concepts that should not be confused with each other. It's around word model. First, we have conceptual models. This means that it is just a set of our assumptions about how we describe system, how we want to model it. And it could be formulated just by words. Then goes mathematical model, where we define our assumptions using set of mathematical equations. And after that appears numerical model, which is computational implementation of our conceptual and mathematical model. And usually for the implementation of these numerical models, we use some specific software. And at the end, we obtain numerical results. So here you can see that we could describe uncertainty of our numerical assessment at 3 different levels. First level will be scenario uncertainty. The second level will be conceptual uncertainty. And then at the level of individual models, they will be parametric uncertainty. So let's start with scenario uncertainties. For scenarios, the step of identification of uncertainties will be explicit description of scenarios that we want to model. This means that we need not just describe the scenario as a story, but we need to decompose it. We need to present it in the form of specific assumptions about how the process will run and how we want to model them and what we want to assess in the end. Usually, there are several types of scenarios. First of all, we develop the scenario of normal evolution, which means that we simulate how the system will behave itself by design. Just as we planned, just as we decided at the beginning, and everything will be ideal. This is basic scenario or scenario of normal evolution. Then we need to develop one or more often several alternative scenarios. And they should not be confused with what-if scenarios, because alternative scenarios are still very realistic. They treat the system as the real system, but for example, the most common example for alternative scenario is faulty containers. Assumption that some small fraction of containers with radioactive waste will be faulty. This is on one hand not a catastrophe. It could happen, but we need to be sure that in this case, in this alternative scenario, our system still will be safe, and our conclusions from our safety assessment will still hold. On the other hand, what if scenarios, they could be unrealistic. We could develop some scenario with, I don't know, totally unpredicted volcano or even spaceship crash, but these scenarios, what if scenarios, are useful, could help us to estimate our system only if we develop them on purpose to demonstrate the robustness of some of subsystem of barriers, or demonstrate significance of some safety function. So for what if scenarios, we usually do not simulate the whole evolution of the system, but we just test some subsystem and try to find if it's robust. And another distinguishable kind of scenarios is human intrusion scenarios. Again, we try to design our disposal facility to make it uninteresting for people, but of course we cannot predict people behavior for such a long term, so we need to estimate potential hazard even in the scenarios where the repository became somehow interesting for the future people. So the great problem in the scenario development is that we need to somehow demonstrate that our analysis is complete. We need to make sure that we did not forget something, that we considered every relevant for safety factor, and for this purpose, the international community of experts developed so-called features, events, and processes list. And this is catalog of all possible factors that are relevant to deep geological disposal. And they are classified both by type. You could find their features, which are properties of the subsystems, events, and processes. And another dimension of this catalog, another classification, is by subsystems. So we could analyze external factors, and we analyze the factors inside the repository system, the factors related to the waste package, the factors related to the system of engineered barriers, the factor related to the geosphere, and the factor related to the environment and people. This is again small remark here. Sometimes I hear that people treat this FEP list as a document with requirements. This is not exactly true, because requirement is only one, to consider this FEP list. But this document itself is more like a catalog, more like a library system, where you could find all possible factors, decide if they are relevant specifically for your site, specifically for your project, and then if this factor is relevant, then you need to proceed with numerical assessment for this factor. So how people compose scenarios from these features, events, and processes? There are several approaches. For example, one approach is when you divide the whole repository system into the elements, into the subsystems. For example, engineered barriers, radioactive waste itself, and factors of human control. And then for each group of factors, you consider that a system is undisturbed by design, and this is initial state, this is basic state. Another state is when some of these subsystems is partially damaged. And the third state for subsystem is that it somehow completely disappeared. And then when you combine these possible states, you obtain set of scenarios of different degree of optimism, and then you could say that you considered more or less all relevant variants, and then you could proceed with numerical assessment of each scenario. Another approach, it's a little bit different. You again divide the system into the subsystems, but then you compose so-called interaction matrix, where you combine elements of this huge system pairwise and consider on each intersection influence of one element of the repository system to the another. Unfortunately, the approach, all of the approaches for the scenario development require very deep involvement of the experts. Even with modern computational technologies, you could not just generate and assess all variants, all the scenarios, and then numerically quantify all of them. So we rely on expert judgment, but not in numerical assessment of the scenario, but in the justification that this is relevant scenario, this need to be assessed, and this set of scenarios is sufficient for the complete description of our system. And another problem with automation and digitalization of scenario analysis is that a lot of factors that we need to consider, we don't know probabilities for them because, again, we deal with slow processes and rare events, and we could not just calculate the probability of the event that our repository will somehow collapse. Because we have not information for the probability of initial events. And this is the difference between analysis for deep geological repository and, for example, nuclear plant. Because for nuclear plants, you could obtain these probabilities of faults of some subsystems of elements. So let's go to the next level, the level of conceptual uncertainties. Again, we need to go through our steps of uncertainty management. First, we need to identify them. For conceptual uncertainties, this step will include explicit consideration of alternative models. Examples of alternative models could be different set of considered processes or different approach of to description of the same process, and even formulation of boundary condition could be also be alternative conceptual model. So in this case, uncertainty reduction step will be our attempt to narrow down the choice of alternative models. And for this step, we need to compare alternative model. So we could not assess conceptual uncertainties if we dealing only with one model. We need several models and we need to compare them. There are several mathematical approaches to the model comparison, but first of all, we need to remember that in safety assessment, we use iterative approach. So we use simpler models on early stages when we maybe have general understanding of the system, but not enough site-specific data. And then when we obtain site-specific data, we could proceed with sophistication of our models based on site-specific data. And there are also a couple of approaches of multimodal analysis where you could express the complexity numerically using the number of parameters, number of outputs, and information criteria. There are also approach where you do not select the ideal conceptual model, but you use all of your alternative models, and when you need numerical assessment, then you use some average numerical assessment for the whole ensemble of these models. Issues with conceptual models, with management of conceptual uncertainties are the following. First of all, as with scenarios, we cannot provide the whole, the exhaustive, the complete set of alternatives. We are dealing with a priori incomplete set of models. And in practice, there is also another catch that a lot of alternatives models appear not because experts analyzed whole set of potential assumptions and developed several models, but very often in practice, alternative models appear due to differences in software that are used for the modeling. And finally, we go to the level of separate numerical model, and this level is pretty straightforward. Uncertainty identification at this level will be outlining the set of uncertain parameters and ranges for their variation. The numerical assessment of resulting uncertainty also straightforward. We need to vary uncertain input parameters and then provide statistical analysis on the outputs that we obtain using this sample of uncertain inputs. For quantification of parameter significance, we could use sensitivity analysis. And for the reduction of parametric uncertainty, of course, we could go to the experimenters and ask for new, more certain parameter values, but also we could use adjustment of parameters by means of parameter optimization and model calibrations. I'll talk about these steps in the next couple of slides, but here I'd like to discuss how the uncertainty management software works in general. You could very often hear about some uncertainty assessment software that it's model independent software. What does it mean? When we analyze uncertainties of the computation model, we need two computational packages. First package, we need the specific software that models our processes of interest. And the second, we need uncertainty management software. How they interact? We need some executable, and we need some input files where we could change the parameters of our model. When we change parameters of our model, we run it with this set of parameters, and then we need to analyze corresponding file or output file and extract our quantity of interest and analyze it. So the uncertainty analysis program usually works in such way that you have some template of input file of your process modeling program. Then at each step of analysis, you fill this template of input file with a new set of parameters, and then you run this program. You obtain a new set of output files. You extract from these output files your quantity of interest, and then using this sample of inputs and sample of outputs, you carry out uncertainty analysis. So the most simple part of this is just uncertainty assessment. So you vary uncertain inputs, you obtain corresponding outputs, and you could analyze the distribution of these outputs. On this slide, you could see different visualization of output uncertainty because it will be very when we deal with outputs of different dimensionality and so on. Again, tiny but very important remark that it is impossible to assess parametric uncertainties if we run our model just once. We need repeated calculations to obtain meaningful statistics. And if we cannot, for some reason, run our models at least 1,000 times, this statistics will not be good. And the common name for this approach is Monte Carlo method, but I do not recommend to use this term because it's very generic term, and usually you from the title of the paper, Monte Carlo analysis of some model, you cannot say what analysis was performed. It's a very, very generic term. The common feature of all of these methods is that you stochastically vary something. So the next part, more interesting in my point of view, is sensitivity analysis. Sensitivity analysis in general is quantification of influence of input parameters on simulation results. Again, we need the sample of different variants of input parameters, different combination of input parameters. We need to run repeated calculations with these variants of parameters, and then we analyze both inputs and outputs to measure the share of each parameter in the output uncertainty. Sensitivity analysis became in last decade, I suppose, very large and separate discipline, and there are a lot of research in the field of sensitivity analysis. You could classify a task that sensitivity analysis is dealing with, for example, by questions that you ask about your model. For example, in some situations, we need so-called screening. We need to identify the parameters that are not significant for our numerical simulation. They are not influencing our output, so we need to identify them, and then we could just fix them at nominal value, and we our result will not change. Another task of sensitivity analysis is parameter ranking. When you need parameter ranking, you are more interested in most significant parameters for your model, and when you get the sensitivity analysis results, you, for example, could try to somehow obtain new information about these significant parameters, but you could prioritize your research. You will not try to obtain some insignificant ones. Other maybe more exotic tasks for sensitivity analysis include variance cutting, when you try to reduce the spread of the output below the chosen threshold. You could need factor mapping when you need to identify the exact regions of input parameters that produce some critical values of your model. And also sensitivity analysis could be used for trend identification and a lot of more specific tasks. The formulation of the sensitivity analysis question, the sensitivity analysis task is important because for different questions we could use different methods, and some methods are more useful, for example, for screening, but not very useful for parameter ranking. So before I begin to list methods for sensitivity analysis, I'd like to say how not to analyze sensitivity. You could hear less often recently, but a lot. You could hear a lot that someone calls sensitivity analysis something like the situation where we assess the modeling result in the nominal at the nominal value of the parameter, and then you get the result at the, for example, value of the parameter 10 times larger, and then result for the times less. And here our sensitivity analysis. Don't do this. Because even for two-dimensional model with two parameters, this is ineffective way to explore the parametric space. There is so-called curse of dimensionality, and data tend to be more sparse in higher dimensions. And if you just analyze some perturbations around value of the one parameter with fix another, you lose a lot of information about the behavior of your model and correspondingly behavior of your system. So how to analyze sensitivity correctly? Actually, you could start very simple. Simple if you vary parameters through the all parametric space, you could analyze sensitivity even graphically. You just plot outputs of your model against inputs, and you look at them and see that, for example, here in the left upper corner, you would see that values of the output are almost independent of input Z1, and at the lower right corner, you could see that values of the output are clearly increase with increasing the value of the parameter. So if you have sufficient sample of stochastically generated inputs and corresponding outputs, you could make some conclusions even without any sensitivity indices, just looking on the scatter plots. The way to describe, to quantify the previous plots is, for example, correlation sensitivity analysis methods. You could just describe the behavior that was on the previous slide by correlation coefficients. The only problem is that will work only with linear or at least monotonous models. So if you have nonlinear models, you could see the lower row of these scatter plots. The correlation coefficient for all of them will be 0 despite their differences. So we could use correlation methods only for linear or quasi-linear models. And for nonlinear but monotonous models, you could use rank correlation methods. Another approach is generalization of this deprecated one at a time method. But if you not just disturb each parameter at a time once, but generate the trajectories of these output perturbations and select the trajectories in the parametric space that lie far from each other, then you could estimate sensitivity using elementary effects. This method named Morris, and this method is pretty good for screening of model parameters, and it requires not a lot of model evaluations, but unfortunately it's almost never reliable when we need to rank most influential parameters. The golden standard of today's sensitivity analysis is so-called variance-based sensitivity analysis. The idea of variance-based sensitivity and Sobol indices in particular, that you could interpret the uncertainty of output of your model as a variance. And then you could estimate share of variance that are related to the parameter itself, and share of the variation that is related to the influence of parameters, including all of its interaction. What does mean interactions? It means that not all of models are additive, and for a lot of models, the share of the parameter when we vary it alone and share of the same parameter when we vary all parameters at the same time will be different. So the total indices are for share of the parameter with all of its joint influences, and main or first order indices is for influence of the parameter on its own. I should mention that usually variance-based sensitivity analysis required specific sampling of the input parameters. It is conditioned by the intention to obtain more, at the same time, more homogeneous sample, but at the same time, this sample will, should be still random. So you could usually generate just simple random samples. You could use Latin hypercubes, and then the quasi Monte Carlo samples could be generated to more homogeneous filling of the parametric space, and it was shown that this strategy of sampling provide more robust results. You obtain reliable sensitivity indices with smaller samples than when using latent hypercube samples. And as I already said, that variance-based methods are considered as golden standard of sensitivity analysis. But there are situations where they are not suitable. This is situations where we could not describe the uncertainty of our output using variance. For example, you could look at the plot in the middle of bottom row, and for this sample, for this parameter, the variance will be not adequate description of output uncertainty. In these cases, another method could be used, so-called methods of probability density methods, which use for measure of sensitivity, for measure of uncertainty, conditional and unconditional probabilities distributions. And the general takeout from this description of methods that before you perform the sensitivity analysis, you need to ask yourself several questions, and depending on the answer, you could select different methods that will be more useful in your particular case. So questions to be asked before sensitivity analysis are the following. What is quantity of interest? First question, and it's very often omitted because sometimes people come to us and say, like, I need to analyze sensitivity of this model, and this model gives output of 10 files. In each of 10 files, you see 10 rows with some values, some list of values, some time series, and the result of sensitivity analysis for each of these quantity will be, can be different. And before you analyze sensitivity, you need to decide what is your quantity of interest, what quantity do you need to analyze. After that, you, of course, define uncertain parameters and their ranges. And then if you have any additional information about your model, it could help you to decide which method could be suitable for your case. Here some example reasoning about method selection, but I already could see that I could easily add another 10 methods to this slide. So the final step of the uncertainty management of the model is model calibration. This step is a little bit different from uncertainty and sensitivity analysis because in sensitivity analysis, we generate the input sample at the beginning and then just analyze the corresponding outputs. During parameter optimization, we generate new points in parametric space using the information about how our model, how our simulation result fits to some available experimental or field data, and we decide where we go where we move in this parametric space to obtain the best fit of the model and the data. One aspect of this process is that here you could see the example of objective function for the optimization. We will at each iteration, we will calculate it and analyze if we moving towards the increasing objective function or towards the decreasing. We need usually to minimize objective function because we need that our model fits our data as close as possible. But you could use for the description of this proximity of your data and your model different functions. And of course, the results that you obtain during the optimization will differ with different objective functions. And here, the movement of the our point is in parametric space. This is defined by optimization algorithm, and there are a lot of them. And very, very quick step into the history of optimization methods. Of course, at the very early stages, we just used brute force search, just randomly search or search using grid, just brute force the combination of the parameters and checked if model fits better using this set of parameters. But even in, I don't know, 3 dimensions, this approach could not be effective. You have no such computational capabilities, and very soon the gradient-based methods appeared. They very fast. They were used a lot, but they have a problem that to use them to descend using knowledge of our objective function gradient required the differentiability of our function of our model. And not all of the models that we meet in our practice are differentiable. So then the gradient-free methods appeared. They did not require the differentiability, but unfortunately, as well as the gradient method, they were local. What does it mean? They depend on the initial guess. So if you put your initial guess somewhere in the wrong parameter combination, then you could never obtain the optimum. And the next idea was, what if we run our optimization a couple of times, but every time we use random initial guesses. And I suppose this led to the development of heuristic optimization methods. The general description of them is that these are just strategies to move point in the multidimensional parametric space, but these strategies usually imitate some natural behavior, some idealized biological or physical or social system, and these methods could be used for global optimization. They also doesn't require optimized function to be differentiable or continuous. So here a couple of examples of this inspired by nature optimization strategies, and I will not describe them in the detail. I have no time for this, but why? The obvious question, why that many? Why we just cannot decide that this method is the best and use them now and for all? Unfortunately, there is so-called no free lunch theorem of optimization, and it reads that there is no general purpose universal optimization strategy, and each method could be good, each method could be better than just brute force and better than other methods, only if this method is specialized to the specific problem at hand. So if we don't know anything about our specific problem, then our most obvious choice is to try optimization with different methods and see what each of them gives us. So questions to ask before model optimization. Again, we need to define variable parameters, and if we know something additional about them, again, we need to decide what is our quantity of interest, what is our output, and also, and here it's more complicated than sensitivity analysis, we also need to decide how we want to measure discrepancy of our simulation result with our actual data. And also there could be different small but significant questions like are simulated outputs appears at the same points with the observed data, or maybe we need some interpolation. Also, if we know that there is sufficient accuracy for our task. Maybe we do not need to overfit our model, and we just can stop our optimization earlier. As I said, a lot of software for uncertainty management is positioned as model independent and universal, and in theory it's true, but there are some real world issues that abstract us for using universally model independent software, because in practice we meet a lot of small but significant issues, starting from different format of inputs. So to provide the data for the universal model independent software, we first need to understand inputs and outputs of specific modeling software, and then after this we could use these universal methods and universal software. Another issues in practice include already mentioned dimensionality of the our output. I already mentioned that even simple visualization for them will be different, but also when we begin to analyze, for example, sensitivity, we need to decide how we want to deal with these multidimensional outputs. For example, do we want to assess influence of each parameter at some specific points, or we need some integral assessment of influence of this parameter, and so on. Another huge practical issue is method choice. As you already guessed, the choice of method is conditioned by a lot of factors. Model properties, model computational costs, and for the optimization, even worse, because we need to try several heuristic algorithms to understand what is good for our particular model. And I also already mentioned that you could use different methods for sampling of input parameters, and this is also the choice of method. So when we try to design our universal model-independent software, we deal with a lot of questions, because our users want just give us the best method and we will use it. But there are no universally best methods. You need to understand what you want to achieve. And one moment about computational cost. As I said, for sufficient statistic, for sufficient analysis, we usually need the thousands of model realization with different combination of the parameters. And sometimes we deal with such complicated, such computationally demanding models that these thousands of model runs are just unavailable. Our model developer says that you could run, I don't know, 200, maybe 500 of model runs, but that's all. No thousands, no 10 of thousands. And in this case, solution is so-called surrogate models or meta models. This is methods for relatively fast approximation of the computationally heavy models using some mathematical approaches. There are a lot of methods for the meta modeling, including both very basic mathematical approximations and very modern machine learning techniques. But of course, we still need as much of as many of realization as possible, but then we could try and approximate the additional realization of our parameter combinations and corresponding model results using these meta models. And this is a very promising field. There are a lot of research today considering meta models, but of course, again, you need to select method that is good for it, and also you need to remember then when you approximate some complex numerical model, you simplify it, and you may lose some high order information, of course. And I'm almost finishing. This is just an impression of universal, hypothetical, absolutely model-independent uncertainty analysis software. So in the conclusion, I'd like to sum up all my talks and say that of course, uncertainty management is a crucial part of safety assessment, and in particular of building confidence in our safety assessment results. And another point, it maybe was not obvious from list of methods, but I need to highlight that sensitivity analysis and parameter optimizations should not be treated as some final stages of the model development, model analysis, but more like tools for model testing, model adjustment, and the interpretation could help the model developer to enhance numerical model. And as I said, model-independent uncertainty analysis software is impossible. We need to balance, we need to research methods, we need to understand them, and then we need to choose from them. And this leads to my final point, that uncertainty management could not be outsourced for some specialized uncertainty analysts, but it's joint work with model developers, and basic knowledge of uncertainty management is required for all of the researchers that involved in safety assessment of at least radioactive waste disposal, but I think it's crucial knowledge for almost all researchers who develop models and analyze natural systems. I suppose that's all for me. I have a long list of references, but I suppose you will see them when when I upload my presentation. Yeah, and this is just in case my contacts. And I'm ready to answer questions if they exist.
So much for the just I'm curious about when you said that we speak about scenarios for intrusion. Just I'm curious, this is a hypothetical scenario or something happened?
It's more like hypothetical scenarios because when we assess, for example, safety for near surface disposal facility, we could provide institutional control because near surface facilities have less period of potential danger. So you could provide institutional control for 10 years, for even 100 years. But when we are talking about deep geological disposal for high-level radioactive waste, we are talking about thousands of years, and you just cannot be sure that your fence and your that this would stand. So we need to assess a possible hazard for these cases. Of course, we design, there are specific requirements for deep geological disposal facilities for siting of them. For example, they should not be some mineral resources near, they should not be some national parks, they should not be some cultural sites, but you never know. So you need to assess this possibility.
You said that the multi-value analysis is very generic word.
Yeah.
So what's you recommend if I need to search?
I recommend that you search more specific names of the methods. For example, Sobol indices for sensitivity analysis, particle swarm optimization method, and so on. Because if you just write Monte Carlo analysis, I don't know, maybe you find some paper on quantum physics. It's possible.
What time for running this data sheet for the data? Maybe hours, days, how many?
For the running of the analysis, it's depend on the complexity of models that we analyze. Because, for example, if we analyze chemical models developed by frequency modeling software, which I suppose a lot of people present here are familiar with, then it's very computational light models, and you could run the analysis in minutes, maybe hours, but not much. It's feasible on your laptop and it's easy. But when we speak, for example, about thermomechanical models, it's a lot of computations. It's very detailed. Very detailed models with a lot of cells, and such models runs even one run of this model could take a couple of hours on the computational cluster. Not your personal laptop, but some more serious computer, and we need at least couple of thousand, couple of hundreds, but better, the more than better. So it's that's why I mentioned meta models, because sometimes our model developers just could provide us couple hundreds of realizations, and we need to do something, extract all available information from them. Thank you.
It's hard to find every useful serial for more than 1,000 years. So the experiment judgment is very important for developing scenarios. So my question is, what's your experience do you have in this area?
You mean in scenario development? It's a very complex question, and I'm not sure that I have a ready answer for this. Of course, we have a lot of experts, but our group, we try find a way to systematize the knowledge, to try to organize this expert knowledge in some comprehensive way, and this is ongoing research, because for example, maybe you're familiar with ISAM methodology from AAA. So these figures, these approaches, description of approaches for systematization of scenarios, they are adapted. One moment. These approaches, they are adapted from AAA documents, but we still rely on experts a lot. We want to help them. We want to outsource some of boring organizing activities to computer, but we still rely on experts very much. Yeah. We have actually in our information system we have small workflow for dealing with FAP list. We could use the international FAP list, then we could select factors or parts from this international FAP list and put check marks on factors that we want to analyze in more details, and link them to the references, and try to combine this analysis in a more organized way. But again, all concerning scenarios, it's work in progress, because of course we have FAP list, we have scenarios, but the argumentation of the completeness of this analysis is ongoing work. No more questions. Thank you very much.
There is a question online. There is a question online. Hi, can you hear me?
Yeah, we can hear you.
Oh, you can hear me. Okay, thank you. Now, just that I couldn't hear some of the questions from the floor. So I hope I won't repeating any that were asked. But I wanted to find out about the, I suppose, the radiation transport codes that you use. are they in suit, meaning are they designed by you, or you just use general codes that the world uses, like I suppose Monte Carlo codes?
I'm not hear you very well, but if I understand you correctly, we use for most of our analysis the codes developed by our institute. From the external codes, we have our code for groundwater flow and transport modeling. We have our code for thermomechanical modeling, but we have our code for our part for uncertainty analysis. But we use, for example, a generic software like FreeQC. For some of our tasks, we use GoldSim for integral models, and that mostly all. Another codes are developed by our institution.
Okay. And I was wondering, for radiation transport, which codes do you use for that?
For the flow transport, we use GERA code. It's developed. If you send me the letter to my email, I'll send you a link on to the page with all our codes.
Okay.
Thank you very much for the question.
Thank you so much. All right.
No more questions.
Unas superiores teachers.
Да, перерыв.
У нас перерыв. Okay. Спасибо.
Не, давай. Блин, это цеплять. Hello, dear friends, dear colleagues. My name is Natalia Kuzmenkova, as I told you before, during the practice. I'm working with environmental radioactivity here on radiochemistry division. And I will tell you about environmental monitoring system. And because Vladimir is a little bit ill, I will continue with destructive analysis of radio for analyzing samples, environmental samples. We will have a 5 minutes break between 2 lectures. And after that, you will have one more lecture from my colleague. Okay, environmental monitoring. I think that this point is very close to most of you because you are working in nuclear enterprises, and every environmental monitoring is very, very similar to each other. And I just want you to show some details, maybe some interesting details, and to explain the reasons why we should be absolutely careful when we are working with the environmental monitoring. Man-made radionuclide sources in the environment, they flow to the Earth through the nuclear facilities, working and incidents and other sources. And of course, intensive development of nuclear technology of both military and civil purpose in 20th century resulted in release of radionuclides to the environment. I think everybody understands and knows that the radioactivity was open in 1895 year. It was only 130 years ago. And before that time, people doesn't understand and cannot count the time of living of environmental. And you can imagine then 150 years ago, people thought that the material, the environment is dead and it doesn't live. And only because of radioactivity open, we can we have opportunity to calculate the time of life of environment. It was very, very, very important. And if the radioactivity exists only 130 years, the environmental or handmade artificial radionuclides exist only 60 years in the planet. When your grandfathers or grandparents got born, then didn't know anything about radioactivity because artificial radionuclide didn't exist on the planet. It is very interesting. And nowadays, our generation have opportunity to make interesting researchers according to environmental radioactivity. And we can develop this area of environment, and we should do it. And because a lot of questions is open now. And here I want to show you a comparison of the amount of radionuclides released in the environment from various sources. And you can see that the main source of man-made radionuclides released in the environment include previous nuclear test explosions in the atmosphere and activities of radiochemical plants for spent nuclear fuel. For example, plant Mayak, Hanford, Lahag, and other radionuclides, other enterprises. Monitoring around nuclear facility. This is a simple scheme, how it works. But the important thing that environmental monitoring was born only in 1953, when the first examples, first accidents, first explosions had been done. And it was developed as a science only after the Chernobyl accident. And nowadays, it is on the peak of its development because of Fukushima accident. And because of Chernobyl and Fukushima, nowadays scientists thinking that it is impossible to the explosion like Chernobyl and Fukushima in the planet. It is impossible to exist. And these lessons was very important for humanity. Radiation monitoring involves the measurements of radiation dose or radionuclide contamination for reasons related to the assessment of control of exposure to radiation or radioactive substances in the interpretation of results. Today, I will not tell you about the individual dosimetry, but it is a very, very important part of environmental monitoring. In the end of lecture, we will tell a little bit. Important that the equipment for environmental monitoring that are used, for example, in Russian nuclear power plants, was produced 50 years ago. And nowadays, nothing new are producing for environmental monitoring. And it is consider the individual dosimetry, the individual tablets, pills. Monitoring programs can be separated by 3 parts: routine monitoring, emergency monitoring, emergency preparedness, and emergency monitoring. And the objectives also are different. First of all, it's compliance with safety standards, long-term trends, control of accumulation in environment, and measurements, air, soil, water, foodstuff, and wipe tests. And here, it is very important to indicate, to catch radionuclides in very, very low concentrations. Most of radioactive monitoring tells us that the activities of radionuclides in these environmental samples are less than minimum detectable activity. But it isn't true. I will show you how many radionuclides during the normal working of a nuclear power plant, for example, is flowing. And the future of environmental monitoring, firstly, is to develop the equipment for indicating low level concentrations of radionuclides. And it is very important also because of emergency preparedness, for early warning. For us, for Russia, for example, and for example, South Korea, it's more important, yes, because if we can indicate the low concentrations of noble gas, for example, we can try to forecast some explosions in the North Korea. And of course, emergency monitoring. This is very understandable. And here in this part, it is very important to develop equipment which will control the highest activity of radionuclides. Because everybody understands that every equipment has limits. And nowadays, we also have not equipment that can catch low-level activities and can indicate very, very high levels. There are very high levels at mean levels that are occurring during the accident. Typical required low limits of detection for gamma emitted under condition of normal operation and emergency situation completed. For example, normal operation and aerosols. In aerosols, we can have iodine 139 2 per minus 10 in minus 4 becquerels per cubic meter. And as I know, and I think as you know, that we usually have in our tables, in our reports from nuclear facilities, the lines with less than minimum detectable activity, and that's it. And of course, nobody knows, maybe you know, why these numbers are here. Why it is exactly 5 in 10 minus 5 becquerels per cubic meter for aerosols. Why? Who knows? Who knows what's the base for these numbers? Многолетний. How many years? Monitoring exists only maximum 50 years and really 30. Really, radioactive monitoring was born after Chernobyl as a system. After Chernobyl, the concentrations and activities was very, very high. Okay, later we'll discuss maybe a little about the numbers. Nuclear power plants in the world. Very interesting. Oh, South Africa. One nuclear power plant. Yeah. Some in Argentina. But you see that we have some continents in the Earth that have no nuclear power plants and no nuclear energy there. And we have some countries with a lot of nuclear power plants. And everywhere where concentrated nuclear power plants, it had some accidents there. Everywhere. Depends the level of the accidents. Somewhere it was higher, somewhere smaller. And as I told you before, only 10 nuclear power plants for all Russia. It is very, I think that it's a pity situation, not very good, because Russia is now creating nuclear power plants in Bangladesh, in Turkey, in Egypt, in Belarus, we created one. But here in Russia, no need. I don't understand exactly, but really we have a project. We have project to create one nuclear power plant here in Vladivostok, for example, and in Yakutia, as I know. Okay, nuclear power plants during normal operation. First of all, noble gases, tritium, and carbon. The most important radionuclides that should be controlled during the normal operating of nuclear power plants. And of course, it is controlled. And for you, it is very important to understand that different reactors, different types of reactors flow out different amount of noble gases and tritium and carbon. For example, here you can see two types of reactors. On fast neutrons reactors and water reactor. And here you can see the contribution of noble gases in the total normalized discharge activity. And you can see that, for example, the carbon is flowing more from water reactor, around 30%. But of course, from 70% to 90% is noble gases. And I think you know well that noble gases are parent radionuclides for some decay products, for example, strontium-90 and cesium-137. And if we control only cesium and strontium, but does not control in good quality noble gases, we will see only the result of the accident. And we cannot forecast or find that point when it when it is beginning. Why tritium is so important? Because we have two sources of tritium in the Earth, natural and technogenic. Tritium is very, very interesting radionuclide and very important because it is not dangerous for person. For example, here in radiochemistry division, one professor, my colleague, drank the glass with tritium. It was around 100 kilobecquerels. And after that, he just had an experiment. And during the day, it was flowing from him 100% during the work day. Tritium is not dangerous for people, or we don't know the effect of tritium now. And if you see in the papers and the articles that tritium affected the strong to the biota, it is not true. Nowadays, we have no proofs that tritium is dangerous. If you have, are you agree with me or not? If you have disagree mine, just tell me. Okay, but really it's true. Tritium is very good tracer, for environmental investigation. Of course, it's a radionuclide and it emits. It has a half-life 12 years. And it is not very easy to catch, to analyze. And we have a natural level of tritium in the Earth that was generated in the atmosphere, lithosphere, and the ocean, and enter into the atmosphere from outside. And technogenic radionuclides, nuclear and thermonuclear weapon test, routine release, and accidents and incidents at nuclear fuel cycle enterprises. And tritium, why I like this element? Because it migrates everywhere. It can go through the walls, through everything. For example, if we open the source with tritium in the second floor, here everywhere will be tritium. And if it is in the high concentration, like in Semipalatinsk polygon, for example, it is very interesting to find how it flows through the river system to the North Pole. Very good marker, very good tracer. And that's why we should control tritium during the nuclear power plant operation, and it is doing, we do it now. For example, tritium released into the atmosphere, and here you can see the permitted level, for example, the green line, and the actual level. And discharges with wastewater into the hydrographic network. of nuclear industry enterprises. It is for different enterprises. For example, Beloyarsk nuclear power plant, Plant Mayak. Beloyarsk also nuclear power plant, it's for water. It's releases, and this is discharges. And for Mayak, you can see that it is below the limits levels, but it exists, and we can indicate that it exists. Medium specific indicators of tritium discharges from European nuclear power plants. You can see here different reactors types. Pressurized water reactor, boiling water reactor, gas-cooled reactor, and second-generation reactor. And you can see that for gas-cooled reactor and the new generation reactors, the level of tritium is higher than for other reactors. But it doesn't decrease or increase during the last 30 years. Okay, total contribution of carbon on tritium and two effective dose from various nuclear installation. Also, you can see different reactors types and how many it flows to the environment during the normal operation. Of course, heavy water reactor wins. Major specific indicators of carbon-14 discharges from European nuclear power plants. Okay, here we can see that water reactor inflows maximum of carbon-14 during the normal operation. It is very important also, I think, to understand, because when you are working in your enterprise, you should absolutely understand what reactor types you works and what radionuclides influence you are waiting from this type of reactor. For example, if you have a water reactor and, or for example, boiling water reactor here, or for example, you choose the reactor for your country, and you should understand which reactor type will influence less than others. And for example, if you have these types of reactor, and you will have this significance of carbon-14, you should understand that something wrong, and it should be noted. Conservative estimate of carbon-14 releases from various sources. Here you can see the carbon and how it increased during the nuclear era, nuclear epoch, from 1955 till 2015. The natural activity of carbon and carbon from nuclear weapon testing. And the same for tritium. And you will see that some days the lines will cross. And for example, if we now using carbon-14 for dating, yes, for dating in archaeology, for dating samples, the method based on that the number of carbon-14 in atmosphere in the Earth are stable during 5,000 years. But the situation can be changed because of nuclear facilities working. And we should add some coefficient to our calculations. Maximum value of radionuclide concentration in Russian nuclear power plants. You see different nuclear power plants and number of radionuclides that are flowing out during the normal operation of these nuclear power plants. This picture, I think everybody knows that to environmental monitoring, important not only the artificial radionuclides, but also, and more important, the natural radionuclides, because the contribution of artificial radionuclides is smaller than for natural radionuclides. And exactly the radon should be monitored in our life everywhere. And it not depends on nuclear facilities and nuclear power plants. The monitoring system and the environmental monitoring system should work not only around the facilities, it should work on the government level. I will show you how it works in Europe, for example. But in Russia, we have no radiation monitoring. We have only around plants and facilities. But for normal, for ordinary life, in some regions in Russia, for example, regions where the uranium produced some days ago, but now closed, now stopped, and the enterprise doesn't work, and environmental monitoring stop. It doesn't work now. And it is very important, and I am absolutely sure that we will have in Russia also, and in your countries, I'm sure that it should be something like digital atlas of natural radiation, like in Europe. You can use this link to take a look how it works. But European Atlas of Natural Radiation, it is very interesting. You can find here in very, very, very detailed information about cosmic ray dose, indoor radon concentration, indoor radon, uranium, thorium, potassium, and soils, terrestrial gamma dose, and others. It is very important how it works. For example, you can here see a European indoor radon map. And if you zoom to some parts of Europe, you will find and indicate all uranium, for example, the places with uranium minerals. And they had also not only radon map in this atlas, and it's absolutely open atlas. Everybody can open and take a look and to investigate the territory. And you will see, for example, Greece here is not very good investigated. I think you should include to this project, be part of that, and to map your territory in more details. But I'm absolutely sure that the future of environmental monitoring in the world is going to this way. We will map all natural radioactivity is natural radioactivity, is nothing nothing special, nothing that can be closed. It's not secret, but it is very important because as I said before, for example, in Russia, we have some territories where some enterprises worked some days ago and now closed, and people are continuing living there. But the situation with radon, for example, is very dangerous. Okay, I think this scheme is understandable for all. Okay, take a look for this atlas. It is very interesting. And for example, the European Radioecological Data Exchange consists of data exchange mechanism and presentation website for radioecological monitoring, which is collected and shared by 39 participating countries. In almost, it is in real time. In real time, a lot of monitors picking in different sites of Europe are pointing the radiation dose in real time. Okay, environmental monitoring content. Of course, as I said before, we should control natural conditions and the state of radioecological knowledge of territory. For example, the Rupur nuclear power plant in Bangladesh that Russia is creating now. Here you can see some points, some locations where the food was bought for indicating the zero level of radioactivity of territory. I think also everybody understands that before creating some enterprise, we should estimate the radioactivity, the natural radioactivity level. And it should include the food and the effect for humanity. How it works? The individual dosimetry is is like a gift, yeah, for people who living on territory for 1 year. And the people are living, are eating, are working with that individual dosimetry during year. And after this year, they collected and calculating the dose. And it is very, very important. About thermoluminescent dosimetry. During the 1950s, now we have no different types of dosimetry. Nowadays, we have only 2 types of dosimetry. It's aluminum oxide and lithium fluoride, who producing in enterprise in a big amount. Of course, we have a lot of laboratories that are playing with different types of pills for individual dosimetry. And we have a lot of patents and a lot of ideas how we can develop this part of radiation monitoring. But only aluminum oxide and lithium fluoride worked. And the situation is crazy because that was created firstly 60 years ago. And I think it is also the part of future of radiation monitoring is to producing some other thermoluminescent dosimetry. And as I said, I know a lot of variations, a lot of investigations about this, but it doesn't work in, for example, in country scale. Air monitoring should include aerosol filters and atmosphere clouds and collecting snow and rain. I think everybody understands that. But that what important? That no need to collect a lot of points. You should just separate the circle to 3 or 5 circles according to distance from the place, from the enterprise, and collect 1-2 points from each area, and it will be enough. Of course, it is important the winds, how it's going, but really for radiation monitoring, for environmental monitoring, no need to have a lot of points. It is the advantage. Soil monitoring. Also, you should understand, and I think you know well, that all radionuclides concentrated in the organic surface horizon of soils. That's why it is important to analyze this horizon of soil to understand the situation. Vegetation monitoring. Of course, most of all, vegetation monitoring is an interesting theme because in one hand, it used like an agricultural part of life. But in another hand, we have some vegetation that are not agricultural, but they are very good indicator for radioactivity. And that's why during the vegetation monitoring, we should be a little bit biologists. And we have the base of database that are telling us in which region, which vegetation are the best for radionuclides accumulation. But before the 21st century, the people monitor only the vegetation that can be eatable. And it is because it is more important for people, for personality. Fauna monitoring, of course, fauna monitoring, you should take and analyze that part of animals that can be eatable, firstly. For example, from fish, it is back of fish. For animals, also it is muscles. The eatable part first, other parts second. Water sampling. Water sampling monitoring is more important. And here, you should take more samples. And it is important to take samples before the enterprise and after. Because if something occurs here, and we find the results here, we cannot understand exactly where is the source. That's why usually, and to understand the current situation, the current operating situation of enterprise, of course, it is very important to take points before and after enterprise. Radioactive monitoring should include the co-precipitation and concentration and separation radionuclides. After the break, I will tell you about separation and concentration in detail. But what I want to say here, in environmental monitoring, the best way to concentrate radionuclides and exactly actinides is co-precipitation with iron hydroxide. This is the best place. Also, during the last 50 years, nothing new. Iron hydroxide works better for all radionuclides and exactly for actinides. Of course, if you take some samples, first gamma and beta estimation, and as I said, you in practice better to repeat measurements through the time. And after that, separation, alpha emitted radionuclide purification. Of course, it should include some steps, and I will show you next lecture. It is not very easy procedure, but it is the most interesting part, I think. Everything because of chemistry, because of radioactive element chemistry. And here you can see how the oxidation state of plutonium and its speciation depends on the pH and the H conditions, for example. And here you can see that different oxidation states of plutonium has different colors. You can see it by your eyes. And it is also very important to understand how to remediate the radiation contaminated territory. And okay, I think I will continue after 5 minutes break, yeah? About exactly separation of actinides. Thank you. So, who would like me to write more? Up here. Okay. All. So, keep in mind, a little sheet of paper, we can write down things, write them to send how many people.
Okay, dear colleagues, I think we're ready to continue. Because Vladimir is ill, I will show you his lecture. I will try to explain ideas that Vladimir had during the preparation of this lecture. But let's try. Okay, destructive characterization of radioactive waste. Continue the theme about environmental monitoring and analyzing environmental samples. In another part, when you're working with waste, everything is more easy, of course, because the activity is higher. And to indicate the radionuclides and the solutions and the compositions of radioactive waste are a little bit easier, more easy than when you're working with low levels concentrations. What we want to know about radioactive waste and why? We don't know the content, the dose rate, the chemical properties. And all of these parameters we should estimate. The content of radionuclides, their amount and types. The basic information, of course, is detection. And of course, during the environmental monitoring and working with radioactive waste, you should use the undestructive analysis, the analysis what we discussed on practice task. And what detectors type should we use? Investigating different radionuclides and different mechanism of radioactivity. Ionization, for example, and for detection of electric current, we can use the ionization detectors, the gas field, the semiconductor detectors, the excitation. And in this type of detecting, we detect the visible light. That have you done in your practice task? You detect the visible light. In semiconductor detector, you detect the electric current. Radiation can produce the defects on the surface. And to analyze this defect, we can use track detectors. And calorimetric detectors we can use to detect the heat or energy absorption. All these methods has advantages and disadvantages, of course. The main characteristics of detector, according to this equation, is intensity, the probability, efficiency. I think everybody knows, and everything depends on resolution of the detector. The liquid scintillation counting. For this method, and of course, to detect the gamma activity radionuclides, no need to make any radiochemical procedures. To detect beta and alpha emitted radionuclides, we should make radiochemical procedures. But to understand well the process, we should understand well the detection mechanisms. Radionuclides plus scintillator can make some disruption to our counting, to the result. It depends very much of chemical quench and color quench effects. All these effects are very important for low level beta emitted radionuclides. And it is not affect to high level radionuclides. To decrease the quench effect, chemical and optical, we usually use different vials. And of course, the glass vial is more convenient
to decrease these effects, but it costs higher than plastic vials. And that's why usually everybody use plastic vials. And we also here in radiochemistry division use plastic vials. The shape of spectrum, why it is important, as I said. For example, for alpha emitted radionuclides with very, very high energy, we can find on liquid scintillator spectrum this picture. And nothing can affect to calculating the activity of radionuclides here. No chemical quencher, no optical quencher. For beta radionuclides, we can see this type of spectrum. And we will have here a lot of effect. That's why we have to estimate the quencher effect to calculate the efficiency. For example, you can see here spectrums for carbon and for tritium. And for tritium, it is also important to understand that the chemical quencher effect or chemical luminescence can close this peak of tritium. And if carbon, you can calculate with more the high efficiency for tritium, it is very important. That's why, for example, nowadays we have problems with scintillator cocktail. Now in Russia, and I think in Belarus also. Because everything that we can prepare ourselves will have this luminescence effect here in this zone of low energy. Of course, if we calculate counting efficiency and quenching, it will help us to have good results. For example, quencher parameter calculating by this TCE. And here you can see how it depends TCE on efficiency for different radionuclides. And you can see for plutonium alpha emitted radionuclides, the quencher doesn't affect because it's alpha radionuclide with high energy, and we can measure it on liquid scintillator with any mistakes. Alpha beta discrimination. Of course, for liquid scintillator, as I showed before, doesn't matter because we can differentiate it very easy by your eyes, because alpha emitted radionuclides will be in the high energy area and beta in slow. But also, I think you know Cherenkov effect that was open I don't remember exactly the time, but because of this effect, we can measure some beta radionuclides directly without any scintillator cocktail. Of course, the efficiency will be slowly. It will be maximum 70% and usually 50%, but it is very convenient to investigate and calculate these radionuclides. For example, strontium 90, chloride 36, and potassium. And for example, for strontium, Cherenkov effect has only yttrium, the daughter radionuclides from strontium, not exactly the strontium. But because they are in equilibrium, we can calculate the amount of strontium using yttrium Cherenkov effect. It is very convenient way to measure beta emitted radionuclides. Also, when you're working with radioactive waste, with high activities, you will never see any Cherenkov effect in environmental samples. Or you should concentrate it from the very, very big amount of water, for example, or soil. This is a simple scheme of liquid scintillator. Multiplier to calculating activity and coincidence, high voltage, how to transform the signal, the light signal from scintillator to the numbers of points on the spectrum. This is the different scintillators that you can find in your lab or in our lab. Not very big amount. We have now only Perkin-Elmer, for example, and in Quantulus and Tricarp, it is also Perkin-Elmer. Also, you can find Hydex, the Finland scintillator counter. And the programs for the software for all of them are similar. Alpha spectrometry with semiconductor detector. The principle is really looks like the scintillator detector when the electrons are stops during the entire to the detector. The alpha spectrometry is very sensitive method, and the minimal detectable activity for alpha spectrometry is 2 orders less than, for example, for liquid scintillator or gamma spectrometry. If you make the purification of alpha emitted radionuclides well, and if you have alpha spectrometer, you can investigate very small amount of radionuclides and isotopes. The spectrums are discrete. We can see different peaks very far from each other, and it is very easy to calculate. And the alpha spectrometry peaks, they has another shape than gamma spectrometry peaks. It is not Gauss distribution. It has some interesting points and a different shape. Okay. I don't know what Vladimir wanted to say here, but about alpha spectrometry. Nowadays, we have only 2 ways to prepare source for alpha spectrometry: is electrodeposition and co-precipitation on the filter. Only 2 these ways, nothing else. And electrodeposition using nowadays in a lot of enterprises, but it is not very convenient because you should clean the this equipment between samples every time. And using filters, you can use it only once, and after that you can waste it. And it is more cheaper and more convenient. And the spectrums are better than during the electrodeposition. Here you can see differences between spectrum of radium with semiconductor detector, for example, and liquid scintillator counter. You can see that on semiconductor detector, you can separate more peaks. That's why I said that alpha spectrometry is a better way to separate different isotopes of one radionuclide. How it looks like, I think everybody knows. Detection of gamma rays. We told about that before. But I think also everybody knows what we have: 2 detector types, planar and coaxial. And here you can see differences between efficiency on planar and coaxial detector. That I said that planar detector can detect this low energy area with X-ray fluorescence. Coaxial detector cannot do it. Energy resolution for germanium detector and scintillator detector. Also how it works. And beta emitted radionuclides on gamma spectrometer. Now you can see the strontium liquid scintillator spectrum and on germanium. You can measure it on germanium spectrometer and also find strontium if you separate it well, and you are sure that in your sample you have only strontium yttrium and nothing else. This is influence of beta emitted radionuclides on gamma spectrometer. And now destructive characterization of radioactive waste. Radiochemistry laboratory should be everywhere in the nuclear facilities and enterprises. But to create this laboratory, you should also create a lot of documents, yes? And the personality should be professional there. And that's why not so many enterprises has radiochemistry laboratories. But the stages of radiochemical analysis includes five steps. It's a homogenization at tracer, and after that sample pretreatment and separation, preparation, the counting source, and measurement. And here in radiochemistry division, we of course can do everything and teach this. Tracers. To calculate exactly the yield during the radiochemistry procedure, you should put in your system radionuclide, the isotope, another isotope of radionuclide you investigated. We usually use for uranium-232 and 236. Here for plutonium-236 and 242. For neptunium is 239 and for thorium 999. And you can see all these peaks. They are not interfere in the alpha spectrometry after the separation each other, and that's why it is very easy to estimate the yield. Sample destruction. In which cases we make destructive analysis, alpha beta emitted, and ICP MS analysis, and adding tracers. You can work with all these type of samples. And how it works. Of course, acid leaching, ashing, acid dissolution, microwave digestion, yes, and fusion, or ultrawave assistant oxidation. And here, for example, fusion, I want to say that all these these four methods, it's also that's it, nothing else you can have to destroy the sample. And to analyze alpha emitted radionuclide and purificate it, you should destroy the sample absolutely totally. 20 years ago, people thought that it is possible just to boil, for example, soil in acid during 2 hours, and every radionuclide goes to solution. But it is not true. Now, scientists understand that to calculate well the actinides, the radionuclides in sample, you should destroy it all, totally. And that's why you have only 4 ways: acid dissolution, ultrawave oxidation, microwave digestion, or fusion. The best way is fusion. And of course, if you work with the radioactive waste, it works because for fusion, no possible to take kilograms of sample or grams of sample. Maximum you can take, as I know, 5 grams. But it doesn't work well. You should take only 1 gram. for good results. And that's why, for example, for environmental sample, it's not very convenient, because to concentrate radionuclides from environmental samples, it is better to take 10 gram, 100 gram. But for radioactive waste, it is possible. This is fusion programs that can work using different solutions for fusioning. But you destroy the sample very, very well. Microwave digestion. I have an experience with microwave, very, very big experience, and I want to say that it doesn't work as well as fusion. After the microwave destroying sample, some particles leaves, and you need to put it to the vial for the glass and boil in acids to finish the procedure to destroy the sample totally. And also it is works for acid digestion. And also acid digestion is very long procedure. The fusion is very fast, but it is very, very expensive. And for small sample, microwave is not very fast, but more faster than just boiling in acids. But it not works 100%. Okay, you destroyed the sample. After that, you should separate radionuclides. And first and the most popular method is extraction. Extraction procedure in Soviet Union, we had a lot of methods how to extract plutonium, uranium, and other actinides from any matrix, any sample. And of course, now it's working. And precipitation and co-precipitation. Usually in your sample, you have not only the actinides or radionuclides with high oxidation states. And before any radiochemical procedure, you have to delete all salts. And for that, for example, potassium, natrium, and other one-valent salts from your matrix, from your sample, it will be very convenient for you for future to separate the high-valent radionuclides. And all actinides and usually are high-valent. That's why better to make the co-precipitation procedure before purification the radionuclide. Also, we can add carriers, because the radionuclides exist in very, very small concentration, even though in radioactive waste, the concentrations cannot be more than 10 in minus 8 milligrams per kilogram, for example. But in environmental samples is less, minus 15, for example. And to separate and purificate radionuclides in good quality, you should add the element, the stable element of the analog of radionuclide. For example, when you separate strontium 90, you should add stable strontium. For cesium, stable cesium. Some radionuclides has no stable isotopes. For example, plutonium. And in that way, we use analogs. For example, neptunium for plutonium and europium for americium. Because, for example, we have no stable americium. For technetium, for example, technetium 99 also has no stable analogs. And that's why we use rhenium for technetium. Why it is very important? Because we have to increase the concentration of element, and it will be better for separation of that element.
during the chemical procedures. The precipitation goals, the removal of interfering radionuclide separation from sample matrix and preconcentration of the nuclide of interest. As I said you before. Okay. Also, source preparation for alpha spectrometry via microprecipitation. We use the rare earth elements for co-precipitation, usually cerium fluoride, but for co-precipitation of actinides and prepare the source for alpha detector, you can use any rare earth element. For example, neodymium and others. They all works well. For precipitation, we have some advantages and disadvantages. The advantages for precipitation is that it is selective and quantitative, and the high degree of concentration we will have. It could be scaled up from milligrams to industrial, and it's simple and convenient. It is really simple. Every student can do it. But we have also disadvantages. For example, the time. We need a large amount of carrier, and precipitate can be contaminated, of course, because the procedure is very long. And it is not very technological. It is very difficult to put it to industry. The solvent extraction or liquid-liquid extraction. Some scientists think that it is the future of chemistry. And it is one of the oldest way how to separate elements, the aim elements from the solutions from the system. And it also has some advantages and disadvantages. How it works, I think everybody understand. First, we use an organic component to catch our radionuclide, for example, and it is very selective method. No need to make any procedures for purification the solution from salts, for example. And after that, after the extraction to organic phase, we re-extract it to the water phase. And this is how it works. First extraction and then back extraction. And really how it works, it is very difficult to make only one extraction procedure and take good results. It is better to create the cascade of columns with extractions, and after the 10th step, the extraction will be 100%. The extraction should be repeated and repeated, and the re-extraction as well. And that's why the process is also very long. But the advantages, it's rapid and efficient, are very selective. This is the very important part for extraction. As extraction advantage is that is very, very selective. The partition coefficients independent of radionuclide concentration. It's technological. It really works on industry. And you back extraction to aqueous system, water system. But of course, after extraction procedure, you have a lot of extragents as waste. And you have to do something to utilize that. And disadvantages is toxic, because during the extraction, you use organic components. Of course, it's toxic. You need large volumes of organic waste. And as I said before, the multiple extraction might be required and affected by impurities in the solvent. Chromatography. A dynamic sorption method for separation and analysis of mixture of substances, as well as for studying their physicochemical properties. We have cation exchange and anion exchange, extra gens or resins. And to understand how it works, we have to understand exactly which complexes create each radionuclide in each conditions. Sometimes, for example, plutonium can create complex with nitrates, but and it is very important and it's ununderstandable. For example, if you have in one solution uranium and plutonium, and you put nitric acid inside, plutonium will create nitric complex, but uranium not. Nobody knows why, but after that, you can use anion exchange resin to separate only plutonium. And it is looks like unbelievable, but anion exchange resin for cation plutonium works when it make complex in nitric acid. Okay. How it works. Of course, also need to make multiply procedures. Here you can see some functional groups for cation exchangers and anion exchange resins. And usually this procedure based on the experience of scientists. Some scientists was found that it is very good coefficient for sorption some radionuclides and exactly this cation on anion exchange resin. It has some advantages. It is simple and efficient method, and also using cation and anion exchange resins are also very cheap because you can buy, for example, 10 kilograms of resin for I don't know, 10 euros. But it will work only for one radionuclide in one condition. It has really high chemical recovery. And it wide range of application from laboratory to industrial, and it's possible separation from interfering counter ions. And the disadvantages, you have to really control pH conditions, because of that depends a lot of things. How complex will exist, how long it will exist, and the creating of complex. Coefficient not has enough for some applications, and it also generates problematic secondary waste as extraction. Extraction chromatography nowadays is the best method. As a functional groups, it's like a combining of extraction and chromatography methods. And as functional group ligands that are used in solvent extraction, and it really works well. Okay, it's the same as the extraction, but taking into account the dynamic mode. And extraction chromatography will have inert support and organic phase. And if you use, for example, vacuum for the rapid separation, you can separate different radionuclides once from one sample very, very fast. The most popular company that produced resins for extraction chromatography is Trischem, France. And these resins are not very expensive. and you can use it together with vacuum box and separate your radionuclides very fast. And of course, if you use extraction chromatography and co-precipitation on the filter with rare earth element, you can make 10 or 12 samples a day for example, 5 or 6 actinides inside. It is very, very convenient and fast. Here you can see some characteristics of resins. For example, actinide resin. And here you can see how it works on different acid solutions for different radionuclides. Here is tetravalent resins, also in different acid concentration. It will work in different ways, and you can use this information for solving your own tasks. This is uranium and tetravalent resin. You can use this resin to separate uranium and tetravalent radionuclides like thorium, for example, and plutonium, if you stable plutonium in oxidation state 4. Strontium resin. This one is very interesting because strontium is one of radioecologically important radionuclide, and everybody use different ways to separate strontium from the environmental samples or from the waste. But the best now is strontium resin, but it is also very expensive. One cartridge cost around 100 euros. Extraction chromatography also has some advantages. It's state of art of the method, high selective individual nucleate columns and high productivity, and some disadvantages. It's expensive, of course. It's toxic, resin bleeding, and it has limited capacity. But no need to have a very, very high qualification to working with the resins. Okay, and summary. The separation needed for the analysis is difficult to measure nuclides. The variety of separation methods available, including precipitation, extraction, solvent extraction, extraction chromatography. Very important that chemical recovery can be measured gravimetrically. Of course, if you have no analog of radionuclides, the another isotope for plutonium, for example, you have no possibility, you have no opportunity to buy plutonium 242 or plutonium 236. In this way, you can use another stable radionuclide and as a chemical tracer and measure it on ICP-MS, for example, to calculate the chemical recovery. And of course, vacuum box can be used to facilitate chromatography separation. And this vacuum box, you can create it yourself. It is not very, very difficult to produce yourself, but it makes your analysis faster 2 times. Thank you for your attention. If you have any questions, please. Last week or 2 weeks ago, we have also school here, and we made with them practice for separation strontium and yttrium. Everybody using extraction, just liquid extraction, simple way, and nobody achieve high quality of separation. And it was really interesting. Everybody was sure that it is very, very easy, but it is not. It is not. When you're working with organic phase, it is not very easy to separate organic and water phases is very difficult. And that's why now here in radiochemistry division, we're using extraction chromatography methods. It's more convenient than others and more fast and more useful. Okay. Uh-huh. Which react? Oh. Noble gas? Yeah, but it's two different sources. Radon is natural, and of course it affects more for people, for biota, everywhere. But noble gases are artificial, and it influence because of nuclear enterprises working. And one of the most important, of course, is xenon, and others, but xenon, I think, the most important one. But of course, radon makes the maximum dose for the world than other gases. But the parent of radon is uranium and thorium. Yeah. Okay, thank you. You have a break till 4:45, as I understand. Who have the tips?
Спасибо большое. Угу. В карманчик, да. Все. So we can begin the last lecture of today. I hope that you are not so tired and can hear me. We will speak about the characterization of contaminated environmental samples. Of course, it means radioactively contaminated samples. And you have got some lectures on this topic. And I will talk about... It doesn't work. Мышкой? Sure. So we will, okay. We will speak about some advanced techniques for characterization of contaminated samples. At first, we will speak about legacy waste samples, historical radioactive contamination, and how it could be characterized using different non-destructive techniques to reveal the forms of radionuclides inside these complex objects. We will speak about autoradiography, electron microscopy methods, Raman scattering, X-ray methods, and some other. Can't work without mouse. So nuclear legacy sites, very complex objects with unknown scenarios of release of radionuclides, of unknown list of radionuclides and activity and so on. And the main problem is how to understand the migration behavior of different radionuclides in different geochemical conditions. If we can characterize so complex objects, we can work with any other. What kind of nuclear legacy we've got in Russia and some other countries? It could be radioactive waste temporary storages of liquid waste, like the Lake Karachay and some other superficial lakes. It could be tanks with the liquid waste, like Hanford site in US, nuclear testing location of explosions, of testing of nuclear bombs in different sites in the world, and some former reactors for plutonium production, which were decommissioned and are to be managed of this waste, special forms of waste. So the first question is, what is speciation of main radionuclides? How is contamination distributed in a landscape scale, macro and micro levels? And how to perform proper sampling to manage this waste properly with low cost and it doesn't like when I go somewhere. And the question is how to choose the optimal set of methods. You know that there are a lot of different methods to reveal the physical chemical forms of radionuclides, different advanced techniques. Some of them are based on synchrotron light. Some of them are based like this X-ray tomography, X-ray diffraction on the laboratory X-ray tubes and electron microscopy transmission. And the cost of these devices is very different and the time for analysis is very different. You are to choose the proper set of methods. It doesn't work. To choose the method of which could obtain the maximum information with the least cost. All the methods of analysis we can divide into 3 big groups according to the presentation of information. It could be
methods for imaging, for visualization, like X-ray, radiography. It could be spectroscopy, where we can see spectrum. Spectrum is the, it's the distribution of intensity according to different energy. And it could be diffraction and scattering, these three main groups. All the methods, all the techniques we can present in this way. So we can see what kind of methods we can use for our purpose. We use non-destructive methods of analysis firstly, before the destructive methods, because we are to reveal the physical chemical forms of radionuclides, to predict their migration in the environment. And after that, we can use destructive methods. So I'm sorry. I see. The first method, non-destructive method, is gamma spectroscopy. We will not speak about now, because I hope that you have got lecture about this very good method. If you have no knowledge about the sample, you can use gamma spectroscopy to see just what kind of activity. Are there only natural radioactive materials or technogenic, artificial radionuclides? After that, we use different methods of local microanalysis, non-destructive methods. First of them is autoradiography, which could reveal heterogeneity of radioactivity distribution among the sample. Then it could be micro-Raman spectroscopy for phase analysis. In some cases, it is very useful. Scanning electron microscopy for morphology, elemental composition of the objects of your sample, X-ray tomography, diffraction, fluorescence, X-ray absorption spectroscopy, and so on. And then we can go to some slightly destructive methods as mass spectrometry with secondary ions and some else. It doesn't work. So we can try to classify all the methods by excitation and recording of signal. You can see here different kind of excitation. There are passive techniques without any excitation signal. Methods by photons excitation, thermal neutrons, electrons, and multiply charged ions. And the signal which we of response, the recording signal could be photons, electrons, protons, alpha particles, multiply charged ions. And what kind of passive techniques we know without any excitation? It could be radiography of different kind, gamma, beta, alpha radiography, spontaneous fission, and so on. And if we use photons, we obtain very good tools for analysis. It could be X-ray methods and laser excitation methods. X-ray methods like X-ray absorption spectroscopy, X-ray fluorescence, X-ray diffraction, and vibrational spectroscopy, which used laser source or some other sources, infrared source like Raman spectroscopy. If we have the response like electrons, it is X-ray photoelectron spectroscopy, which is excited by X-ray source and have the response with electrons. And it is a method of slightly destructive method, ICP-MS with laser ablation. A laser source has very small amount of sample and perform isotopic analysis of this very small part of your sample. If you can use thermal neutrons in reactor. If you have such possibility, you can perform neutron activation analysis and fission radiography and alpha radiography on the base of nuclear reactions. It's a little specific methods, but it could be used for characterization of radioactively contaminated samples. And if you use electron beam, there are a group of electron microscopy, scattering electron microscopy, and transmission electron microscopy, which has the additional possibility of chemical and phase analysis. It could be energy dispersive X-ray spectroscopy, or it could be phase analysis, diffraction of scattered electrons, and so on. And the last part is not non-destructive. It is a little slightly destructive methods, like mass spectroscopy with secondary ions, and Pixie proton-induced or particle-induced X-ray emission methods, which is used for characterization of contaminated samples. So let's begin from passive techniques. How can radiography be useful for contaminated samples characterization? Radiography is a method which is traditionally used for distribution study of contaminated samples, of radioactivity in contaminated samples at macro and micro levels. It is the best tool for searching of spots of local concentration of radioactive contamination. It is very useful if you want to use different local microanalysis techniques like scanning electron microscopy and Raman spectroscopy and other micro methods. You can extract the particle of interest using radiography. And you can estimate the total radioactivity and alpha radioactivity separately if you use different kind of radiography. I will speak about it further. So what kind of detectors for radiography they are? Detectors are very special. It must have special distribution. It is not like gamma spectroscopy detector or alpha spectroscopy detector, which is used for bulk analysis of a sample. Here we used some special detectors with special resolution. The first group is photoplates, X-ray films, nuclear emulsions. You know that the phenomenon of radioactivity was opened using photoplate. So it is one of the ancient detectors for radiography. The second group is solid-state nuclear detectors for charged particles. Both these groups need chemical or photochemical pretreatment of your detector for analysis. Another group is autoradiography with imaging plates, so-called computed radiography or digital radiography. It does not need any photochemical or chemical pretreatment. You have the image just after exposure time. And one of the modern methods, the group of methods are detectors which could work in real time. Semiconductor diodes, solid-state scintillators. In our practice, we use two kinds of detectors: solid-state nuclear detectors for charged particles. We use them for alpha autoradiography, and autoradiography with imaging plate, which could detect all kinds of radioactivity: gamma, beta, and alpha. Detectors in real time is good
sorry,
for...
we cannot see the presentation.
You not see presentation?
Yes.
А что надо сделать? Ага. Presentation. Here it is. Yeah. I close it. Вот эту нужно, вот эту заказать. Да? Делиться. And what is it now? Can you see it?
We can see it, thank you.
Спасибо большое. Окей, мы справились. Мы справились.
Там еще как-то скрыть это можно. Вы через что транслировали? Через его собственность? Ну, получается, через свой трансфер.
А через что надо?
Вот через это.
Нет?
Нет, ну работало и так.
Yeah.
Я так уже включил.
Сейчас мы будем переходить в другое измерение.
Не знаю, кстати. Выключилось, что ли?
Такое бывает.
Есть?
Вот нельзя, но я не знаю, это очень...
Замечательно.
А она без нее никак, да?
Ну, без этого.
А мышью?
Это мышь.
А,
Можно просто презентацию.
Не, ну в крайнем случае сделаем так, но просто хотелось бы, чтобы...
все было культурно.
Да, там и веб-камеры выводятся. Нет.
Ну, тогда придется обойтись.
Тут я смотрю, она у меня не работает. Я пытаюсь листать, вот ей. Вот эта штука вообще не работает. Вот это. Через раз, да? Ну вот как-то.
Ну, видать, села.
Села батарейка.
Это на вас.
Так.
Тогда возвращаемся к стандартному варианту.
А вот это может как-то уйти куда-нибудь? Чтобы хоть что-то... нет, все равно. Ладно, главное, чтобы народ было видно. Только это же не работает.
Да.
Угу. Может, вниз куда-нибудь? Туда. Ее.
Прилепить. Сейчас она должна
Да,
скрываться.
да, все, она должна скрываться.
Но
А как же я буду назад листать, интересно?
чего?
Ну, вот эта штука не работает.
Не
Вот, по-моему, нет.
Не, ну можно
Вот назад мне нужно.
колесом.
Отлично. Все, поняла. Ага. So, I'm sorry. I can continue. What are the advantages of autoradiography with imaging plates? It is very express method, and it could optimize sampling process. When you want to characterize your contaminated sample, you are to use very small amount of about 1 gram of material for different kind of analysis. So we are to choose the most radioactively contaminated part of your waste. And radiography could help you to find this local concentration, local radioactively contaminated part. And it could detect hardly determined beta emitters like tritium and radiocarbon and strontium and so on. Radiography system with imaging plates consists of 3 main blocks: detector, reader, and digital electronics. There are soft screens. Working side is blue, and the opposite side, plastic support, is black. And we used this screen for some exposition time in close contact with our radioactively contaminated samples. It could be soils or filters with the colloids and particulated matter or some plants or some other radioactively contaminated samples. This imaging plate has a sensitive layer which contains crystals of phthalate bromide of barium doped with europium 2+. And the second block is reader, special laser scanner with the laser source, which simulates photoluminescence in the sensitive layer. And the third block is visualization block of the obtained image, which converts the luminescence signal to the digital form. It is the scheme of this process: unrecorded imaging plate, and after some alpha, beta, gamma radiation, there are some latent signal inside this sensitive layer, and after scanning with laser beam, we can obtain the response of this luminescence, photoluminescence in the different energy. And the great advantage of these imaging plates is that we can use it for many, many times, more than 1,000 times, because in visible light we can clean all the information from the previous exposure. There are some physical principles if you are interested in this detector. Some examples of the analyzing, of characterizing of the samples. Here it is, the sands from Semipalatinsk test site. You can see down some bags with the plastic bags with the sand from the place of the explosions of nuclear testing. You know that nuclear testing on the surface of the Earth was stopped in the beginning of 1960s because it was the law, the international law about it, and it is very ancient, very old samples. But you can see that on the radiography image, it is in the upper part of this slide. We can find the traces, the radiography traces of some of these sands. This is the grid with the cesium-137, which could help us to find the places of the most interesting particles, like coordination grid for to search and to extract the particles of interest. Except searching of the particle, we can try to have some semi-quantitative result from this method, because there are software inside this radiography system, and it can measure the intensity of photoluminescence in digital luminescence units. If you use some reference materials, you can calibrate this radiography system. Of course, here I can't say what is the activity, because I don't know the radionuclides. I only see that it is definitely not a simple sand from some clean place, that it is radioactively contaminated. And for further analysis, we can extract the particles of interest and see their chemical and phase composition. The next example is the waste from the territory of Angarsk combine of conversion of uranium concentrate to hexafluoride for further enrichment of uranium. isotopic composition. And the fact is that there was some historical legacy contamination of the territory, of the soils around this enterprise. And the problem is how to manage this waste, how to separate the most radioactively contaminated parts of them. And we analyze different kind of soils. There are some bricks fragments, cement fragments, some remains of wood, and radiography image show that the most part of this radioactivity is concentrated in these remains of wood, which was impregnated with contaminated solutions and are responsible for the dominating part of the radioactivity in these soils around enterprise. So we can optimize the sampling, and we can the first decision, obtain the first decision about the management of these contaminated samples. Another example of the using of imaging plates radiography is the analyzing of aerosol material from Chernobyl nuclear power plant. There are some filters, Petriano filters of different pores sizes. This is the first, and this is second and third filters. And you can see that the distribution of radioactivity is heterogeneous. And the most part of activity is in the first filter. You can see the different in exposure time. We can analyze these particles, these aerosol materials after this radiography analysis. Very convenient part of our work is the possibility to manipulate with our particles, with our samples, using this radiography system. If we have some filter and we are to cut them, to separate, to try to find the particles of interest, in any step we can lose our materials, and we can check if they are on place and see after cutting and shifting what is it inside these filters. Aha. Another result is from a French project. They are to manage some contaminated wall, some building with contaminated walls and ceiling and floors, and they use a lot of around 1,000 radiography images on this wall to find the places of radioactivity contamination. You can see that the most part of this wall is just clean, but some spots, radioactively spots, are there. The fact is that they can't use any dosimeters, because it is not gamma activity, it is some beta activity. I don't remember if it was carbon 14 or maybe technetium, something that have no signal on dosimeter, and the imaging plate, which is very sensitive for beta particles, is very useful for this 2D mapping of radioactivity traces. And the other group of radiography detectors with solid state nuclear detectors, plastic detector for alpha particles. It is very good for our work because you know that alpha emitting nuclides, most of them are long-lived. Uranium, plutonium, americium, neptunium isotopes are very long-lived, and today contaminated waste contain a lot of different radionuclides, including cesium, strontium, and some other dose-forming nuclides, which dose is much higher than of alpha-emitting nuclides. But if we are to predict the behavior of this radioactivity in future for many 100 years, 1,000 years, the distribution of alpha activity is very important. And in this case, using of plastic detector, which could see only alpha activity and more higher in energy. It doesn't see any beta particles or gamma rays and some low energy radioactivity. So it used these detectors use etching, pre-etching chemical before reading, and it can use any exposition time, minutes, weeks, months, due to no fading of hidden alpha tracks with time. So we can reveal very low alpha activity. It is very useful. We can use exposure time for 2 weeks, for instance. This is aerosol particle. And the advantage of this method is that we can see the direction of alpha particles, and we can see that this cluster of alpha particles is concentrated, has beginning in one spot. So it is one hot particle which has very high alpha activity. And if we try to analyze this shape of the track, alpha track, after etching, this is etch pit of latent alpha track, we can see that the form of these tracks is different according to different energy. This is americium 241, plutonium 239, and uranium 235. They have different energy. It is around 5.5 mega electron volt, 5.1 mega electron volt, and 4 and 3 or something like that. And if we use the same etching conditions, the same time of etching, we can obtain something like alpha spectroscopy with micro resolution, alpha spectroscopy of one hot particle, using the definition of alpha energy of one alpha particle. So alpha track radiography is a useful instrument for characterization of alpha emitting nuclides, especially on the background of very high beta activity. If we try to use imaging plate, we can try to use it using some screens, special screen, which can close the alpha activity, but the difference of these radiography images was very small. We cannot see it, so alpha track radiography is the single method for alpha emitting nuclides characterization. Let's go further from radiography to another pool of methods, set of electron microscopy methods. They are based on electron beam using. From here, it comes incident high kilovolt beam. If it is scanning electron microscopy, it is around 15-20 kilovolts. If it is transmission electron microscopy, it is around 200 kilovolt, because the beam is to go through sample in the case of transmission electron microscopy. And on this base of electron beam, we can use different analytical systems. It could be energy dispersive X-ray emission, characteristic X-rays. It could be diffraction of the scattered electrons, so we can perform chemical analysis and phase analysis of your sample with micron resolution. In transmission electron microscopy, we can see the morphology of small colloids and the chemical composition using energy dispersive X-ray emission. Or it could be electron energy loss spectroscopy, and it could be diffraction to phase analysis and so on. So if we remember three parts of methods, it could be visualization, diffraction, and a spectrum, all kind of. What is the difference of different mode of scanning electron microscopy? It could be secondary electron mode in this case, or backscattered electron mode in this case. This is the picture of the images of the same place, but in different modes. Secondary electron mode is good for morphology analysis. It is it has much higher signal, and we can see the details of morphology. If we use backscattered electron mode, the morphology image is not so good, but we can see composition contrast. This is heavy particle, uranium oxide particle, and we can see it very clear. If we compare, in this case, it is invisible. We cannot reveal it. But if you want to find something which is heavier than the matrix, this method is very useful for you. Let's see the difference in morphology when we use electron microscopy, scanning electron microscopy. Different kind of samples are different. This is melted surface of nuclear test site soils from Semipalatinsk test site. You know that there are several places in the world with the nuclear testing on the surface, not in underground, but on the surface of the earth. And the kind of, you can see that the shape is specific. It has some bubbles on the surface. It is melted surface, but the composition is just like sand. It is simple sand, like in Semipalatinsk. This soil, simple soil, but the morphology is not the same. If we compare these morphological images with the hot particles from Chernobyl soils, you can see the typical grains of the fuel particles with the special burn-up structure, you know, intergranular fission gases, roots, and it is backscattered electron mode, scanning electron microscopy. You can see some clay minerals on the surface of uranium oxide fuel particle. So we can see composition, obtain composition results, and morphology results. This is the pumice from the Chernobyl nuclear power plant, the lowest floor bubble basin, number 1. It was full with water, and when Chernobyl lava came to this floor, it formed something like pumice. Like when volcano comes to the sea, there are some pumice fragments. They are the same with big bubbles, but if you compare this pumice with pumice from volcano, you can see that there are some uranium oxides, dendrites in bright color. And on the surface of this pumice, we can see some secondary minerals of uranium-6 hexavalent uranium. So we can see from electron microscopy, we can obtain the information about the forms of uranium. It's not only pumice, but some of uranium is released from this pumice and dissolved and formed secondary minerals, very simple for dissolution, for further dissolution. This is an example from remains of wood from the soils around enterprise of sublimate enterprise in Angarsk. This is the remains of the wood with uranium phosphates crystals on its surface, which was which were grows from the growing from the solution, radioactively uranium containing solution. And except morphology results, we can obtain spectra of X-ray spectra with the, if you use some library or some reference materials, you can see the chemical composition of your sample. And you can obtain some elemental mapping of different uranium, niobium, zirconium, for instance. And you can obtain some diffraction results, electron backscattering diffraction using scanning electron microscopy. If you have transmission electron microscopy, it could be a diffraction pattern for phase composition analysis. Okay, let's go further. This is the example from some basin of liquid nuclear waste from one of the enterprises, Siberian enterprises, and you can see the morphology of secondary minerals and its composition. It is crystals of pyrite crystals and uranium oxide microparticles according to composition and morphology results. And on the upper images, you can see different secondary crystals of sulfides of iron. And here there are some uranium-containing particles, and you can see the different morphology of them. It could be aggregates of small particles. It could be uranium, which is mixed with organic matter. You can see different forms of uranium materials from the waste, from these bottom sediments of basin storage of liquid nuclear waste. Official, which is to be managed. It is waste now. And very good method for express analysis of phases is Raman spectroscopy. It is based on laser source, monochromatic light, and we can see the scattering of this light. And a Raman shift can show us the using fingerprint of using some library or some publications, some papers. You can compare the intensive peaks of Raman shift. And you can see the valence state of uranium, for instance. Uranium oxide could be in different phases. And the fact is that Raman spectroscopy is really used for spent nuclear fuel characterization. We saw this spectroscopy, Raman spectroscopy device in hot cell in Marcoule in France. They use it inside the hot cell where the spent nuclear fuel is cutting and characterizing. And they can see the oxidation state of uranium. All the device Raman spectroscopy is outside the hot cell, and there is only microscope and some optowire with the laser source and the signal using another wire. So it is a real method for spent nuclear fuel characterization. And the advantage of Raman spectroscopy is that we can use transparent some bottle or vial if it has transparent environment. If you have some radioactive materials, you cannot go in any other lab with it. It is not good. But if you close it inside some glass vial, you can go, and using microscope, you can focus on your material, on your sample contaminated, and can analyze your radioactively contaminated sample. It is the example of Chernobyl hot particles, 3 different hot particles, very different morphology and composition. And we use electron microscopy and Raman spectroscopy for analyzing the forms of uranium and zirconia in this zirconium in these particles. The first is just uranium oxide, just almost stoichiometric. And you can see the previous grains of the fuel. It is very slightly changed during the accident. It was found not far from the Chernobyl nuclear power plant, around 1-2 kilometers to the west. Another particle is zirconium uranium oxide with very mixed composition. It has zirconium uranium in different ratio. And Raman spectroscopy shows that it is tetragonal zirconia, zirconium oxide. It is not stable under conditions of the Earth because it goes to the monoclinic zirconia. But in the case of some doping, in this case it is doped with uranium, it is tetragonal. It is important because in some cases this phase could destroy, and it is the form which is not stable under conditions of the environment. And the third particle is just zirconia, monoclinic zirconia with some traces of uranium. And Raman spectroscopy shows zirconia, monoclinic zirconia phase composition. There are some examples, and let's go to X-ray methods. Have you any lecture on X-ray methods? X-ray absorption spectroscopy, no? XAFS, XANES, no? So then I can talk some words about it. It is just some methods which are very important for characterization of the forms of the radionuclides. They have diffraction and scattering, like X-ray diffraction and small angle X-ray scattering for characterization of phases or some forms and shapes. It could do some imaging in some tomography analysis, for instance, and it could do some spectroscopy in different cases. And today, X-ray methods could be realized on the base of laboratory devices, X-ray tube, and on synchrotron light. It is different brightness, you know, and I shall show you the difference in this brightness of the source. But some years ago, we said that X-ray absorption spectroscopy could be realized only on synchrotron light, but now we've got in our division in this building X-ray absorption spectroscopy, which is based on the X-ray tube, laboratory tube. Let's go further and see what kind of methods can we use. So X-ray absorption spectroscopy, just a method for speciation analysis. We can reveal valence state of the element of interest. We can reveal the local structure, the local surrounding of the element of interest. And there are three main regions of absorption spectrum. Pre-H, it has some information in some cases. And the main region is Xanes, X-ray absorption near H structure, just H region, and this region, extended X-ray absorption fine structure region, just some fluctuation of signal. How can we use these different methods? This is an example of Xanes information. It is just valence state. The position of energy can show us the valence state of uranium in this case. There are different particles from Mayak site, from Chernobyl exclusion zone, of different valence state of uranium. Some of them more oxidized, some of them are just stoichiometric uranium-02. Except valence state of definite elements, we can say something about symmetry of the crystal, existence of not full electron shells, and so on, and some else. And this is fingerprint method. So we are to have some library. We are to have some standards to understand the valence state of the element. And the next possibility is the last region after H region. We can perform the Fourier transformation of this region, and we will see the type of neighbors atoms. Not exactly, it is not like EDX, but we can guess if we know something about your sample. You can obtain the information about coordination number with big arrow, and very exactly, you can know the interatomic distances around the element of your interest, the atom of your interest, and some geometric characteristics. Here you can see some examples of uranium analysis of local surroundings around uranium. It could be some complexes, superficial complexes, like uranium-6 on the clay minerals, on the surface of clay minerals. This is uranium-6 on the coal surface, on peat surface. This is uranium oxide, hydroxide, shapite. This is uranium phosphate minerals, uranium phosphate synthesized. This is carbonate of uranyl. This is uranates. And all this information we can obtain from X-ray absorption spectroscopy based on synchrotron light. If you use laboratory spectroscopy like ours, it is difficult to obtain good EXAFS results. We can see something about valence state using XANAs, and the brightness, of course, is not so high like in synchrotron light. But in some cases, it is convenient to go just here to see some results about your radioactively contaminated samples. Let's compare two different devices of X-ray fluorescence analysis. This is the results from our device X-ray fluorescence with micron resolution, which is based on X-ray laboratory tube. The scale bar is equal to 1 millimeter, so it is big particle, which we can analyze and see elemental mapping: sulfur, silicon, iron, and uranium, and compare and obtain some spectra of the composition, of chemical composition. And let's compare these results with the X-ray fluorescence on the base of synchrotron light. The scale bar is 5 micrometers. So it is due to big brightness of this source, synchrotron source. And it is not convenient to go with your samples somewhere. I would like to say that in Moscow, we have no, in Kurchatov Institute, we have synchrotron. And we work there and obtain a lot of results in X-ray absorption spectroscopy, but we have no microbeam line with the micron resolution. So we have to go somewhere for this analysis. It is not convenient. Sometimes we use our laboratory devices. But let's see this example of synchrotron based. It is uranium, calcium, iron, and this is the map which compare these 3 elements and see that uranium has no not mixed with any of elements except oxygen. This is electron microscopy image of the same particle. It is from Mayak bottom sediments from one of the basins, storage of liquid nuclear waste at the Mayak site. And if we use synchrotron light, we can just go from X-ray fluorescence. When you find some particle, you can go to XANA's EXAFS results just on this particle. We can't do that in laboratory device because there are different devices, and it is a very great advantage of synchrotron light. So we can say that it is uranium-6 particle, hexavalent, and EXAFS show that it is Chopite. We can say that we characterize this small particle, not very big. You can see the scale bar, and we can obtain information about speciation of uranium in this small particle. And this is an example of X-ray tomography. X-ray tomography is just distribution of density. It is not elemental analysis. It is not phase analysis. It is just density. So X-ray source comes through your sample, and according to the density, you got such an image. But if you know something about your sample, you can guess what kind of bright spots are in this tomography image. This is the Chernobyl lava fragment from elephant foot. It is around 3 millimeters on 2 millimeters in size, and it has a lot of different crystals, microcrystals inside it. It is not only glass. Lava is a real glass matrix with some crystals. It could be high uranium zirconium with uranium and silicate of zirconium uranium. It could be zirconium oxide, uranium oxide dendrites, different balls, drops of stainless steel, and so on, and a lot of bubbles, of course. Let's go to some slightly destructive method. We go to some of the last slides. Slightly destructive method is the methods which are based on the particle induced particles or protons beam with high energy, which comes on the sample, and you've got different responses. It could be Rutherford backscattering, which can help you to analyze the composition. It could be particle-induced X-ray emission or nuclear reactions for isotopic analysis. And this kind of analysis sometimes are very useful for contaminated samples and characterization. And some words about mass spectroscopy. It is not, it is a really destructive method, ICP-MS, but it can help you to define the source of contamination. If you understand the ratio of isotopic ratio of plutonium or uranium, you can see what kind of source it could be. Because you know that plutonium-240, plutonium-239 ratio depends on the source. If it is some reactors, it could be very different ratio. If it is weapon-grade plutonium, it is just close to 0, because weapon-grade plutonium must be just pure plutonium 239 or something like pure. And if you go to the different nuclear testing, depending on the power of the explosion, the ratio of plutonium 241, plutonium 239, and plutonium 240 to plutonium 239. Here it is 240 plutonium. Depends on the power of the explosion. If it is low power explosion, it is just very small ratio, and a little like global fallout. You know, global fallout is the result of explosions in the stratosphere. It was the idea in some years around in 1950s. It was decided that if we explode our bombs in the stratosphere, it will be okay because it is something there. But the fact is that the rain of hot particles from stratosphere came to the surface, and this is global fallout. We can find the trace of this global fallout in any bottom sediments or soil anywhere in North Hemisphere, and a little smaller, but in South Hemisphere too. And the high power explosions have a little higher ratio, of plutonium isotopes. But if we go to reactor accidents, you can see that here it is explosions, nuclear testing, and the much bigger much bigger range of isotopic ratio is in the case of accidents in the reactor. I think that you understand it because in the reactor, it is a very big time of burn-up, and so it is activated the isotopes of plutonium 240, 241, 242, and the number of the portion of such isotopes is higher in the case of reactor. So we go to the conclusion remarks just in time. I would like to say that the most informative non-destructive techniques for legacy waste characterization are autoradiography for distribution of radionuclides and searching of local concentration of them. There are methods of electron microscopy for morphology analysis, non-elemental composition of contaminated samples. X-ray techniques are very important tool for speciation analysis, structure analysis, phase analysis, tomography, valence state, surroundings of atoms, and so on. And Raman scattering is good for phase definition in some cases. And the next step is destructive methods analysis, including sequential extraction techniques, which needs the dissolution, the total dissolution of the sample, but we can perform the partitioning of your sample and see the different distribution of the radionuclides on different forms. And I think that it is. Thank you for your attention. Here we go. Just thank you. I'm sorry if something is not good in our technique. Okay. Maybe some questions.
I have a question about bit 42 when we comparing plutonium ratio to know which grade is what grade or something like that. I see this in a vertical, the ratio of plutonium, but what in horizontal?
The ratio of plutonium.
This is
plutonium. This is plutonium 242 and plutonium 239. Yes. This is plutonium 241 to plutonium 239.
Yeah, so the same for accident and webbing rate is the same.
No. No, you mean the first picture? The first picture, it is just only one axis, only one axis in the first picture.
Page 42.
No, yeah.
And my second question about the thing we comparing the composition and the density. This is something regarding to the efficiency. If I need to compare or just to if it's composite and density or composite only or morphology only. So can you give me some insight about the efficiency if I need to compare or just morphology and composite?
So you want to see only morphology?
If I need to see morphology, so maybe I take second electron microscope, but morphology and composite, maybe I take back stepping. So no different in efficiency between them, or
efficiency for morphology. You know, really, there are some detectors inside. This is the tube electron beam, you know. Here it is the secondary electron detector. And just close to the sample, there are backscattered electron detectors. And you can see in the same time, well, change, you can change this mode. Yeah, they are working together, together. If it is no questions, so thank you.
There is a question online. Hello?
Hello.
Can you hear me? Okay. Can you hear me?
Yes, yes, yes.
Okay. It's a question about the electron microscopy. I just didn't get the difference between, is it the secondary electron mode and the tertiary electron mode?
What is the question?
I didn't get the difference between the secondary electron mode and the tertiary electron mode for electron microscopy.
You mean what is the difference between this different mode? Well, there are different detectors.
Okay.
Very different detectors. And secondary electron has very high signal because there are a lot of. I can draw a picture, but I think you cannot see it. Secondary electrons. What is the mechanism? When the primary electron beam comes inside your sample, they excite the secondary electrons from your atom. There are a lot of secondary electrons, so the signal is very high. But the same electron from the primary beam can scatter inside the sample and go back. This is backscattered electrons. So its energy is lower if the density is higher. That is why a uranium particle is bright white and carbon materials are black because these primary electrons lose the energy in density matter. So backscattered electron detectors are very close to the sample to have all these very rare. The number of backscattered electrons is very low. But this is very informative for our composition. I don't know if it is clear.
It makes sense. But I just wanted to find out in terms of application, because I understand it's different beam energies, right, for secondary and tertiary, right? You have, I think it's like 20 for secondary and then 200 keV for tertiary. So I'm just wondering, in terms of the material that you're analyzing at the point, what determines which mode are you use? Basically, which mode are you going to opt for?
I'm sorry, could you repeat? What is your question? You ask about the energies of the
tertiary. Yeah, secondary and tertiary. The difference is the electron beam energy, right? The primary electron beam energy.
The primary electron beam, now we talk only about scanning electron microscopy. It has acceleration voltage around 15, 20 kilovolts. This is primary electron beam.
Electron beam, yeah. And then for tertiary, it's about 200, right? So I'm wondering, in terms of the scanning, I suppose when analyzing the material, what determines which mode are you gonna use? Secondary or tertiary? Which beam, how do you select which beam energy? What determines, what determines which beam energy are you gonna use? That's my question right now.
I don't understand your I'm sorry.
Okay, no, it's not a problem. Thank you.
Can you come maybe tomorrow? We will speak because it is not. It is very hard to speak in such way.
Okay,
I'm sorry.
all right, not a problem.
Uh-huh. Я почему?
Вот он между там.
Ну, просто.